Good morning, everybody. Welcome to our presentation. Today, we will summarize the effort that we have been working on for the last 6 weeks. We are addressing multilingual and code switching in speech recognition. My name is Ahmed Ali. I work at QCRI in Doha, and I've been working with lots of colleagues, scientists, principals, PhD student, undergrad, trying to address multilingual and code switching. Just, we have been working hard over the last 6 weeks. Previous then we had 2 weeks courses, but the effort started a few months before that. We had our first proposal in December last year. After the success, we formed the team, we get together. Our first meeting was in Doha in March in QCRI. The second meeting was in May in Edinburgh. We had a few visitors from the team who are unfortunately not able to be with us today. We had Shamur from QCRI, Peter Bell from University of Edinburgh, Buvana visited us, Nizar Habash from New York University. Unfortunately, they couldn't stay until the last day. So we are we are working on multilingual. We also have a multilingual team spread nicely across the globe. As you see here, we have 4 from the US, from Johns Hopkins and CMU. We have 4 from the UK, from the University of Edinburgh, 3 from Qatar, 5 from India, from different labs. We have 2 from France, 2 from United Arab Emirates, and 1 from Hong Kong. So as you can see, we always work 24 hours during the last 6 weeks. So our interesting meetings, we always have a 12 hours time shift. So whenever, any time of the day, it is convenient for somebody. So looking at the labs, we have a nice distribution between academic and industry. We have QCRI, Johns Hopkins, the CSLP, and the Human Language Technology. We have Carnegie Mellon, the University of Edinburgh, New York University, and IIT in Bombay. And from the industry, we have help from multiple places. Canary helped us with some data in Arabic and code switching in real cases. We had help from Microsoft Research in India. They give us Telugu data and annotation. And we have Ravi from Uni4 has been helping us in data and also trying to do some of the experiment in the acoustic models. So before moving forward, would like to acknowledge those who have helped us to reach this stage. QCRI has offered us very nice computing power, CPU and GPU. We have been enjoying them for the last 6 weeks. Hopefully, we'll have more access to run some of the experiment until ICASP or other venues coming. Microsoft Research in India has helped us to fund the Telugu data. We are working on this, and thanks to JHU for financing the dialectal Arabic to move forward. So here is the structure of the talk. We split it into 6 sections. The first part, I will talk about introduction to code switching in ASR, why it's important, why I would like to address this, and some of the challenges. Hopefully, by the end of this session, you will be interested in code switching. I assume if you are here, you already have some interest, but we'll address some of the challenges that may not be obvious in the code switching. And then we have a colleague who has more linguistic background, will tell us more about the experiment and the effort they have done into studying why code switching is happening. Code switching is a phenomena that requires building a good machine learning, and machine learning, deep learning needs a lot of data, and we are always lacking data, and we'll talk about data generation. By the end of the day, we are speech people who would like to build some models, so this will be the core part, or will be one of the interesting aspects now, how we build the models given these 2 limitations we have. Now, we understand that code switching is interesting, but we don't know really how to visualize it, and we'll talk a little bit more about how to present it and how to address it. At the end, we'll talk about the summary and future look. And, if you bear with us until the end, we promise to have some good news for those who are interested to do more about code switching. Right, so I'll go into the introduction. Briefly, code switching is a mixing between the 2 languages or more. And here we are looking beyond borrowing a single language. So if I say I'll Uber it in Arabic or I'll Google it in Hindi, this is not really what we are addressing. We are addressing more where people switch between 2 languages or more. I mean, more, we'll see some interesting examples about more. But obvious cases where people switch often between Arabic and English to the extent they give it a name called Arabizi, or Hindi and English, they call it English. in other cases, you see the change happen in different cases, either in formal scenario, like in Arabic, when people giving a formal presentation, or in a social scenario where people are bilingual families. So it happened in some cases informal, in some cases in casual. But actually, what's really interesting, and this is what we have to be paying attention to, is code switching rare. It doesn't happen often. So if we take a sample of the 900 hours, we may have 2 or 3 hours of code switching. So it's not common to have a code switching. But when it happens, it's important. It happens in a medical scenario. It happens when people forget their, the language they have learned. I mean, we cannot afford to lose it. When you have a patient-doctor communication, when there's a teacher L1 and L2. So it's rare but important. I mean, there are more and more practical scenarios happening where I work in Qatar. There's a World Cup happening in a couple of months where we expect a couple of millions to come to the city where the population is 2 million, right? God knows what will happen. So you do expect these people would require to communicate. So there's no chance you're going to say press 1 for English, 2 for French, 552 for whatever language, right? This is something that now the machine should be able to expect this in language recognition. But also, when you go to dialectal, when you go to multilingual, we always forget that when you go to this direction, you are addressing the dialect as well, because now I'm not speaking formal, I'm going back outside of my comfort zone. So if I'm an Arabic speaker, there's a very good chance when I go to code switch, I will go to my dialect, and Amir will talk about how can we address the dialectal change when it comes to code switching. And there are a lot of reasons for this to happen. So this is a couple of nice examples. Here it shows code switching in multilingual and reality. So there is 15 ways in Arabic to write Happy New Year. So there's 35 to 40 ways of pronouncing that. This is just a simple thing. And speaking about India, the best example to say the land of languages, where there are 30 languages or more with a different script. So the problem in practicality is important. So this is an introduction for how code switching, how we address it in our workshop. So there's an environment around us that, due to some reason in the environment, I will code switch. Although I'm an Arabic native speaker, but for some reason, when I meet with Amir and Angie, we all switch to English. We don't know why this is happening. We're all Arabic native speaker, but there's an environment around us. And then we'll end up generating some audio, would like to recognize, like to model this audio. Ultimately, at the end, we'll have some text we need to visualize. So I'll say something interesting about the text, but this is an example of the text happening. So I say something in Arabic, followed by something in English, followed by something in Arabic, followed by something in English. Today, my talk morning about, I mean, it doesn't sound right. If you look at the second line, this is as English as wrong, but this is how I said it in Arabic. So what happens here, when I do code switch, do I mind the language rule or I make my own rule? So do we follow the linguistic rule of code switching, or the speech is happening? And we will hear more from colleagues who generate fantastic code switching text. I mean, when the humans like it more than real, and when they put it in action, we start to see something different. So speaking of the environment, after my talk, my colleague will emphasize more on the linguistic background, Electra, and Damishmita and Daniel will talk about why code switching is happening. We'd like to understand what's the reason for code switching is happening. And when it happens, how do we characterize it? How do we measure the number of code switching is happening in the text? Do we measure the pauses? Do we measure the acoustics? Where is the information of the code switching? And would like to understand, is it in the lexical information or in the acoustics? And if we understand something from the lexical information, can we take it to the acoustics? How much of a social aspect is impacting us to do code switching? Has it been because of colonization, or because we go to another brand, or we travel? There are a lot of things. And what's actually very, very important, I'm not sure how much we have addressed in this 6 weeks, but definitely you are interested in carrying this forward. We understand we played with a set number of languages, and would like to generalize what we have seen so far from these languages moving forward. So if we study code switching in Arabic English, can we take it to Telugu English? I mean, we generalize this in cases. And of course, the best example is the South African, where you can see in single utterance 5 languages with a code switching. I don't know how this happened, but colleagues assured this is a real case, and we have examples of studying this. Now we understand the environment, or we have made an attempt to understand the environment. Now the interesting part, or the exciting part in what we do, is we try to model the speech and try to understand. And how can we recognize code switching? And we look at it in three different efforts. The first effort in data, because we know that we have 1,000 hours of Arabic, 1,000 hours of English, 2 billion words of Arabic, 2 billion words of English, but maybe you will lucky to have 5 hours in Arabic, English, or a little bit of tweets here and there from code switching. So we try to use semi-supervised to generate data, to crawl YouTubes, to crawl something and augment it. We use self-supervised. Most of the pre-trained model try to leverage it, and we augment data, and we have done some interesting work in the data augmentation. We'll hear about it. For the acoustics part, we try to see how can we efficiently model code switching, because think about it, it's a graph. You have seen a lot of data, so you can build a very strong language model. Then I do expect that after today, my talk about, or my morning talk about, you don't expect this pattern. So there's a switch in the graph between L1 or L2 or multiple L. So we have some effort into this. We have colleagues look at efficient decoder. We have colleagues who looked at which point in the search you look for the code switching. How can we do with and without the text? And at the end, once you build a system, you look at it and say, oh God, what's this, right? Just you have something in Telugu, you have something in English. Word error, it's giving you 80%, but is this really 80% or is this something less than this? So this is one of the things that we have been looking at. When we'll show you today some interesting tool that we are releasing, ASR, compare eval, and Andre will talk about it. And at the end, we'll generate some text, right? But when you generate some text, do we have a say on this text, how it look like? So when you have the word Washington, right? Washington as Arabic, as the Arabic word, right? More than many Arabic words, right? Then how do we evaluate? See how we evaluate the ASR? We try to ask ourselves a previous question: how we understand the code switching ASR? Because because when you go from L1 to L2, potentially you are introducing a new language where you have the prefix from the Arabics, the stem from the English, and the suffix from the Arabic. This is a new how we penalize the ASR for this. So what we did, we introduced the human acceptability for an ASR output, where we ask the human, would you be able to accept this output as it is for me to visualize on the screen? And we are in the roadmap or for having human readability of the code switching output. And we have a very interesting results where we see, sometimes we don't really have to care that much, and I will not ruin the findings. We have some interesting finds in how can we get from the orthography, how can we deal with all of these changes into the output. Also from the phonetics, we can look at the phonetic similarity between the L1 and L2, and also the semantics. We happen to realize that the semantics is very helpful when it comes to this stage. So these are the three areas that we have addressed. And at this stage, I will hand the slides to Electra to tell us more about characteristics, characterization, and prediction for code switching from a linguistic point of view.
Hi everyone, I'm Electra Wallington from the University of Edinburgh, and I'm going to be introducing the work that's been done by one of the sub-teams within the code switching group, whose focus has been not on the building of systems to deal with code switching, but on the analysing the code switching data itself. That is, what type of variation are we expecting to see in code switching data, and why is this variation taking place? So just to reiterate, the overall aim of the code switching group is to develop systems and build and methods to deal with code switching during ASR. Now, that's great, but code switching isn't this monolithic phenomenon. It's very, very variable, and it's best to illustrate that through some examples. So here are 3 snippets from what all claim to be code switching data sets. And it's probably obvious to people pretty quickly that though these are all like code switching examples, the style of the code switching, like what constitutes code switching, is very different. So if we look at the Scottish Gaelic English sentence first, though there is both English and Gaelic in there, the English is very, very constrained. It's just one singular noun phrase in the middle of an otherwise Gaelic bit of speech. Turning to Hindi English, there's a lot more English, but it's similarly constrained in terms of what the English is being used for. And then in stark contrast, if we look at the Xhosa English example, these kind of constraints disappear completely. There are long spans of Xhosa, long spans of English, and the two languages seem to be quite similar in the kind of syntactic and semantic function. So why is that variability important? Well, if we weren't to consider the fact that code switching is variable, and we just went ahead and tried to tackle code switching ASR, then we'd very likely run into problems of domain mismatch. So that is, if we trained a system on any of those code switching data sets I just showed you, then yes, we'd probably find a system that could work very well at handling one type of code switching. But would that system generalize at test time? Would it be able to cope with different styles of code switching in different bits of speech? Probably not. So this is why, alongside the development of models, it's important to actually characterize and predict code switching behavior. So to break that down a bit, by characterizing code switching behavior, I just mean trying to quantify those stylistic differences I picked up on earlier. So what type of features actually make these distinctions? Is it, the frequency with which speakers switch between languages? Is it the choice of a speaker to stay in one language for a certain length of time? Is it the syntactic or semantic roles of the two languages? So the fact that there is this variation also gives rise to a higher level question, which is what's actually causing what is causing this variation? Are there specific higher level variables that affect or predict a specific style of code switching? For example, the languages involved, the speech setting or domain, characteristics linked to the speakers. So for the next couple of minutes, I'm going to talk more about the characterizing of code switching, and then we'll pass on to Dami and Debasmita, who will talk more about predicting code switching. So the first thing to say is that this idea of trying to quantify or measure differences in code switching style across different data sets isn't novel. Metrics have already been proposed in the literature that do this to some extent. So our first task was to do a systematic investigation of these metrics, asking things like, what exactly are they measuring? Do any of them in isolation fully capture these stylistic differences? And if not, are they complementary? Can we use them in combination to characterize code switching behavior? So to actually introduce the metrics themselves, so first is this M index. Now this is quite a intuitive but also quite naive measure of just the amount of code switching in a data set. All it does is it looks at the amount of tokens of the two languages and looks at the ratio of them. So a higher M index means that there's an equal amount of, say, Spanish and English tokens. And this therefore means that that data set has more code switching in it. The I index has a similar intuition behind it. It's also trying to measure amount of code switching in a data set, but it does this by instead looking at the number of switches there are from one language to another. And what's quite striking and interesting about this is that though these two metrics at a high level are trying to do the same thing, they're both trying to quantify just amount of code switching. Depending on which metric you use, you'll end up with very different results. So if we look at the Spanish-English example at the bottom, according to M index, this is a sentence that's very rich in code switching. There's a lot of Spanish, there's a lot of English. If we think about it in terms of I index though, it's actually a very poor code switching example. There's only one transition from English into Spanish. So burstiness and memory are two other metrics that have been talked about. And these care less about, these are less about measuring absolute amounts of the two languages in a data set and more to do with how these two languages interact and are distributed. So I'll focus on memory here. So memory is all about looking at the correlation in terms of length of spans in the two languages. So a negative memory means that we're likely to see long spans in one language, followed by a very short span in the following language. A positive memory in comparison means that the spans of the two languages are going to be equal in length. So in order to investigate this these metrics, we had to first collate a wide range of data sets, and we had to be really careful to make sure we tried to cover as many different languages and domains as possible. So language-wise, we tried to consider data from Spanish English, Mandarin English, Indic English, Arabic English, Scottish Gaelic English, and South African English. And like I said, we also tried to cover a range of domains, so conversational speech, TV speech, technical lectures, traditional narrative, read speech, and media broadcasts. So to turn to some analysis, here I've plotted the M-index across 4 different Scottish Gaelic English datasets. Now, it's important to say that despite the fact these are all Scottish Gaelic English datasets, they are varying in domain. And importantly, MG Alba is a far more conversational, spontaneous type of speech than the rest of them. What's also striking is that according to M-index, this has by far the most code switching. And this is intuitive, right? We would probably expect a more conversational style data set to have more instances of code switching in it. So far, so good. But what happens if we look at another metric? So here is the memory scores for the same 4 data sets. And the key takeaway here is that actually these 2 metrics are really not monotonic at all. It's not the case that the data set that comes up as the most rich in code switching according to M-index, that doesn't transfer across to memory. And so the lesson to be learned, what this is really proving, is that in isolation, any of these metrics are somewhat meaningless. We really need to be considering them as a collective. So when we do that, does this help us compare different code switching styles? Potentially. So here are 2 Mandarin English data sets. On the left, we have some speech from technical lectures, and on the right, we have a conversational data set. And now I'm plotting all 4 metrics against each other and looking at the overall shape of the metrics. And personally, I think there's quite a striking difference between these 2. So on the left, if we look at the scores for the technical lecture data, we have fairly high M-index, fairly high I-index, and then this massive decline corresponding to a really low memory score. On the right with the CME data, again, starting with quite high M-index, but importantly, the line gets shallower and shallower as we tend towards memory. And what this is telling us, or why this is useful, is that these metrics seem to be doing something in terms of showing up different code switching styles across 2 different domains, right? It could be the case that these shapes are suggestive of the type of code switching we'll see in formal lectures versus conversational speech. So what I've just showed is that these metrics could be good for something. It is worth quickly acknowledging some pitfalls of these metrics. First of all, they all are based on counting tokens. They work at the token level. But the notion of what actually is a token, what we should be taking as a token, will differ across languages. They also require language IDs at the token level. This isn't trivial, so often we need to do some upstream language identification, which could introduce a lot of errors. And the final thing to say is that these metrics claim to be language independent. They claim to be usable to compare data sets across languages. And due to the fact there are subtle typological differences, I doubt whether that's the case. And for time constraints, I won't go into this point, but feel free to ask me about it. And then finally, a similar but different question is, are these metrics sufficient? Are they actually doing enough to capture all the differences we want to be capturing? So just as a final point, here are 2 snippets of data again. And just based on those metrics I've been discussing, Hindi English would probably show up as having lots and lots of code switching in it. Very frequent switches, equal amounts of English and Hindi. But unlike the Spanish English, we have these kind of constraints in terms of what the English is actually being used for. This is what I talked about previously. The current metrics are agnostic to syntactic or semantic role, and the code switching literature tells us we really shouldn't be if we want to define code switching. So I'm now going to pass on to Danny, who's going to talk a bit more about predicting code switching.
Hello, everyone. My name is Danielle Cartagenis. I'm from the University of Illinois at Chicago. And I just want to kind of really get into the predicting the code switching behavior, right? So Electra had talked about the characterizing code switching, we want to predict it. So we know based on linguistic literature that there are a lot of things that can affect code switching. Some of these things are speaker characteristics, right? That includes age, generational differences, gender, identity expression, and there's actually a lot more that we could consider. But I want to just get into age and gender. So these were some of the two characteristics that we really looked at. And we also looked at formality, but one of my other colleagues will get into that later. So just to talk a little bit more about the corpora that we used the Bangor-Miami corpus. That is the Spanish-English corpus of bilinguals from Miami, right? It was conversational. It's probably mostly Cuban Spanish, but it wouldn't be the only type of Spanish, taking that there are a lot of Hispanics in Miami. We also have the CIMI corpus. So that was the Mandarin English. It's also conversational and it's mostly university students. And then we have the African soap operas. As you can see, I have a soap bar singing opera. So it included Zulu, Zoha, Xhosa, Setswana, and Sesotho. So let's look a little bit at age. So as Electra said, she mentioned the M and the I index, right? Those were two of the metrics that we really looked into. So our Bangor-Miami corpus actually was one of the few corpora that kept track of age. So looking at age and looking at the M and I index, right, we can see that there is a little bit of a trend, right? The trend line declines just a little bit here for both M and I index. M index is blue, I index is orange, but this wasn't statistically significant, right? At least from what we were looking at. It's the same thing for our memory, right? So you can see that there's a trend line. It declines a little bit as age increases, but again, not statistically significant, right? So this could be one of two things, right? It's either age is not necessarily a strong factor, or it's really indicating that the metrics we're using to characterize the code switching may not be sufficient in capturing the stylistic differences that we are looking for, which is something that Electra touched upon earlier, right? And then here we looked at gender. So more than a few of the corpora actually kept track of gender. The SOAPies also kept track of gender, but I didn't want to put it up here because it was just a lot of data and it was a little messy to look at. So we're just looking at the Mandarin English and the Spanish English. So you can kind of see that there are some differences between gender. So the middle color is male and the lighter color is female for all of the corpora here. And you can see that there is some difference, but again, these weren't statistically significant. So as I said before, is it because the metrics aren't as they're not as sufficient in capturing the code switching that we are looking for, right? One of the other things that we really looked at was formality. And so I will pass it on to my colleague, Depasmita, who will get into more detail about formality.
Thank you. Hi, everyone. My name is Depasmita. I'm an incoming PhD student at Columbia University, and I'll now be presenting my work on predicting code switching with a focus on formality and code switching. As you've already heard from Electra and Danielle, we as a sub-team wanted to find out what higher level factors influence code switching behavior in order to be able to predict code switching from those factors. One of the factors that we did a deep dive on was formality. In this deep dive, the questions that we were interested in answering were, what role does formality play in code switching? And is this role universal and language independent? In order to answer these questions, we conducted a preliminary study into text and speech-based formality of 3 multilingual code-switched corpora. Our ultimate goal was to extrapolate our findings to be able to predict the amount of code switching in an unseen corpus or domain from its level of formality. Domain level formality in particular would be quite useful for understanding and anticipating possible formality effects on code switching in a new domain ahead of any experimentation, particularly for low resource languages or language pairs that we don't have data for, which is often the case with studies of code switching. So, why did we choose to look particularly at formality? For starters, formality is a characteristic of language production that is universal, so any work done on formality can, in theory, be extended to new language pairs, speech settings, and data sets. Also, whenever we speak to other people, we adopt a specific register or level of formality. So, domains can be treated as having an inherent and stable level of formality to an extent. For instance, speech from broadcast news in any language tends to be quite formal, whereas telephone conversations between friends tend to be more informal. In addition to this, when it comes to code switching, we have some intuition about the kinds of situations in which it is more or less acceptable to code switch, how in different situations we're likely to code switch in different ways, and how formality might inform the kind of code switching we perform. In this way, a focus on formality draws indirectly on speech setting and speaker relationships, which are also possible factors that influence code switching as a whole. It is worth noting that formality itself is quite a big topic that hasn't been covered much in the literature, whether in relation to code switching or otherwise, making it ideal for a preliminary investigation. The key question of our work here was to define and measure formality of text and speech. According to one of the few existing studies of formality in text, formal language is more precise, structurally complex, and context independent than informal language. And while an expression can be more or less formal compared to another, no expression can be absolutely formal or absolutely informal. A corresponding empirical measure of formality is the FM score, which is put forth in the same previous work and is the measure that we use throughout our investigation for text-based formality. The FM score is based on the distribution of part-of-speech categories within a corpus, as certain parts of speech lend themselves to more precise and unambiguous language, whereas others are needed to produce more implicit and involved language. This leads us to the following simple formula for calculating the FM score on a corpus, where the more formal parts of speech are the ones highlighted in blue, and the more informal ones are highlighted in orange. The FM score can then vary between 0 and 100%, with more formal corpora getting higher scores. Aside from formality in text, there have also been a couple of studies on measuring the formality of speech. The authors on this side collectively found that features including speaking rate, pitch, and loudness were indicative of different levels of spoken formality, specifically when looking at the variation in the features rather than their absolute values. Here, greater variation in any one feature is linked to less formal conversations. In our work, we focused on variation in speaking rate and pitch. The data that we used came from multilingual code-switch corpora in Mandarin, Spanish, and Scottish Gaelic, and consisted of interview-based and conversational data where speakers code switch on occasion. I'll mainly be focusing on the Spanish-English results in this presentation. So throughout this work, we assumed that a conversation or a corpus has an established level of formality to it, which can be measured effectively on its monolingual segments. This established level of formality can then be used to analyze the formality of the code switch segments of the corpus. We incorporated this assumption into our workflow for text-based formality before performing part-of-speech tagging on those subsets of the data. For Scottish Gaelic in particular, we used a specialized tagger that was kindly made available to us by Will Lamb's Gaelic Research Group at the University of Edinburgh. So following tagging, we simply computed FM score according to its formula. We began with a number of baselining experiments in order to calibrate the FM score metric on monolingual corpora of known formality. We found that informal corpora, such as the switchboard corpus, had FM scores of about 40%, and that more formal corpora, such as broadcast news and US Supreme Court proceedings, had FM scores of about 70%. We also found that within the switchboard corpus, random subsets of the corpus had consistently similar scores, and that within the call home corpus, both Spanish and English monolingual transcripts had similar scores, despite being in different languages. This was also true for Mandarin and English within a multilingual broadcast news corpus. We also did some baseline experiments on multilingual TED Talks and found some interesting results that come up again in our own experiments. So here with the Spanish-English TED Talks, the talks were originally given in Spanish and later manually translated into English. In this case, while the FM score in either language is similar to the other, Spanish consistently had a higher score, which might have something to do with the syntax of the language compared to English. We observed a similar effect, but in the opposite direction with the Mandarin English TED Talks. Overall, from our baseline experiments, we found that the FM score metric seems to work reasonably well across the different languages that we're focusing on and across different levels of formality. So to complete our calibration of the FM score metric, we computed it on our chosen code switching corpora. Specifically, we wanted to see whether the FM score would be consistent before and after automatic translation of the monolingual segments of the data. We found some interesting patterns in what happens when we start with monolingual Spanish, then translate to English, and then back to Spanish, and vice versa. So starting with monolingual English, translating to Spanish, and then back. As was the case with our baselining experiments, sorry, can we go back a slide? Thank you. So as I was saying, as with our baselining experiments, identical English data has a lower FM score than its corresponding Spanish data, and back translation to Spanish actually increases the FM score compared to the original value. This effect is also visible in the opposite direction, with back translation to English also increasing the score compared to the original value. We observed a similar effect on the FM score when looking at the Mandarin English data, where identical Mandarin data had lower scores compared to corresponding English. So there are a couple of effects at play here. One explanation for these observations is that the FM score has some inherent language dependence due to the differences in the natural distributions of parts of speech in different languages with differing syntax. So Spanish might use more articles to express the same meaning as in English, resulting in a higher FM score in Spanish than English, for instance. Another effect at play, however, does seem to be that of machine translation alone, where automatic back translation seems to alter syntax to a significant enough level that then indirectly affects formality measurement. So overall, in addition to seeing that FM score works reasonably well, we get a sense of how it might depend on certain language-specific properties. Having established that the FM score works on monolingual data, we next tested and found that it also works on code switch data across all three of our corpora, as all of the resulting FM scores are on the informal side, matching our prior knowledge and expectations. Now that we've covered the highlights of our text-based investigation, I'm going to pivot back to the acoustic side of things, starting with the experimental setup. So for speech-based formality, our workflow involved computing speaking rate and pitch at the utterance level in each conversation in the corpus using scripts written by Jay and normalizing to a 0 to 1 scale. As with the text-based metric, we began the speech-based experiments by performing calibration on corpora of known formality. Our baselining experiments confirmed that greater variance in speaking rate and pitch do indeed correspond to more informal speech corpora in general. Next, after calculating variance in speaking rate and pitch across our code switching corpora, we lined these results up with what we already had from text and combined the scores to create an informality ranking, where a greater score corresponds to more informality. We chose to combine these because we think that the text-based FM score encodes information that is complementary to and independent from speech-based acoustic scores, and we hypothesized that combining the two media would help provide a more complete characterization of formality, which could then more reliably be used to investigate relationships with code switching for later prediction. As a starting point for our ultimate goal of predicting propensity to code switch, based on the formality of a corpus, we investigated whether there was any correlation between the overall formality of the corpus and the amount of code switching present. And we did this according to known metrics for measuring the amount of code switching. I'll focus on the M-index metric briefly, which is the token counting metric that Electra mentioned earlier, but note that the following results generalize fairly well across the other code switching metrics as well. So as you can see, we found a positive correlation between how formal a corpus is and how much code switching is present in the same corpus. Although the correlation is quite weak, it is statistically significant. And given this significance, the weak correlation might just be a result of the ranking system we used. And so we plan to retry this analysis with the raw scores for text and speech-based formality. We also think that it could be fruitful to try multivariate logistic regression here with features other than formality, as it could be that formality does influence the amount of code switching, but only when interacting with other features such as topic or speech setting, for instance. While we're not absolutely sure to what extent formality and code switching are dependent on each other, we do at a very basic level see what we expect, which is promising. Overall, this finding acts as a good starting point for further refinement of formality metrics and provides some insight into which methods of measuring code switching align well with measuring formality. Overall, the key takeaways from our work on characterizing code switching are that while existing code switching metrics complement each other and capture some stylistic differences, they do need to be amended to actually become language independent, particularly because current metrics are too coarse to capture the nuances of stylistic differences. When it comes to predicting code switching, text-based F-scores work fairly well on monolingual and code switch data, but not perfect due to slight language dependencies. Similarly, speech-based variance scores seem to work too, but the weak correlation we found between overall formality and code switching suggests that there is room to further refine speech-based formality too. Going on to our future work, a few main directions that we think would be good, as we have alluded to previously, would involve developing code switching metrics that are not agnostic to linguistic aspects, refining formality metrics, and investigating how topic interacts with formality in code switching, as well as other potentially influential factors. That's it for me. Thank you for your attention. I'll hand it back to the team.
Thanks, Dabashmita. So by now you have heard from our colleagues who have been working on the language aspect. So this work package, just saying a couple of words, we were not expected to have an improvement in the error rate or having a higher perplexity. The motivation here was to understand why code switching is happening. We're pleased to see one of the efforts for formality have gone a little bit further in understanding. We have collected a wide range of languages. We looked at different ways to measure formality and code switching in different languages. At this stage, we understand a little bit about code switching. We haven't gone very far, but we have one way to move forward. We'd like to go next based on what we have understand from the language. Can we, based on this knowledge, understand, generate some data? And at this stage, we're going to look at text, and Preeti will tell us more about the effort in generating text. So thanks to the group in the linguistic.
Okay. Hi, everyone. Good morning. I'm Preeti Jyoti. I'm a faculty member in the CSE department at IIT Bombay. And this coming module, we'll be focusing entirely on generating synthetic code switch speech. Next slide, please. Yeah, so as Ahmed already mentioned, so code switch text is a scarce resource. It's hard to get access to large amounts of code switch data. And to compound the problem, the code switch text is structurally very complex. And there's a lot of diversity in how code switch sentences are rendered. So next slide, please. So there are three broad directions which we investigate to tackle this challenge. So the first is, can we borrow insights from linguistic theories to guide the generation of synthetic code switch text? What if we have much larger amounts of parallel text in the matrix and embedded languages, but if you have a much smaller amount of real code switch text, how do we make effective use of? And lastly, when we have very powerful pre-trained models, which are trained on monolingual text, can we bootstrap on top of such models and then use them along with constraint generation to generate some synthetic code switch text? So next slide, please. So these are all ideas which are synergistic. And so in conjunction, they could be used to further improve the quality of generated text. So here's a very quick overview of the presentations to come in the next slide. So first, we'll have Amir and Inji, who will talk about linguistic theory-based techniques and lexical replacement strategies for generating code switch text. Then Bara will talk about using pre-trained models to do the same. And finally, we'll wrap up with Jay and Brian, who will talk about how to use end-to-end sequence-to-sequence models and parallel text to generate synthetic code switch sentences. So with that, over to Amir.
Hi, everyone. My name is Amir Hussain. I'm a PhD student here at Hopkins. And I'm talking about linguistic theory-based code switching text generation and its practicality in speech recognition. So the main motivation of this work is developing ASR for code switching is extremely challenging because of the data scarcity, grammatical structure complexity, and domain mismatch. So we propose a morphological enhanced text generation pipeline for Arabic English code switching. Why Arabic English specifically? Because of its richness in dialects and morphological properties. So previous approaches explored the code switching text augmentation to improve performance on NLP downstream tasks. In this work, we investigate the effectiveness of code switching text augmentation for improving ASR performance, specifically in a zero-shot learning, where we assume that we don't have code switching from real data. So the proposed approach starts with dialectal text translation. We use transformer MT that was fine-tuned on a lot of dialectal data. We perform morphological segmentation, since Arabic is a morphologically complex language. Then we align the parallel text, the Arabic and the translated one, using either fast align or fine-tune the embed. We generate the parse using the Stanford parser. And once we have the alignments and the parse, we can generate code switching text either with linguistic constraint, like equivalence constraint, or just with random lexical replacements. Once we generate the candidates, we can sample from them either randomly or based on the prior for switching point fraction. This is just an example of the importance of morphological segmentation for alignments. So you can see with just word square level alignments, most of the morphologically complex words are misaligned. Once we use segmentation, those issues are resolved, but with fast align, we have extra noise with alignments. When we use embed, we fine tune it on the parallel text and do the alignments, we resolve all of these issues. So what is equivalence constraint? Basically, it states that code mixing can only occur where the surface structure of the two languages map into each other, which means implicitly we're following the grammatical rules of the two languages. So here an example, we start with the English parse. With the alignments, we can project this parse to an Arabic, and you can see there is the reordering of some words. For example, the political situations becomes situations the political. And once we have this projected tree, we can perform replacements and generate code switching. And this is a very interesting example. Because we're using morphological segmentation, we end up with this interesting example. We'll start with the Arabic morpheme L, which means the, and then we follow that by the English phrase political situation. This is an example of a very natural code switching in Arabic language. So for the data sets for ASR, we're using TDM3, which is a monolingual English data, MGB2, which is the standardized Arabic data. This we call baseline. Then we use a variety of standardized Arabic plus a lot of dialects from different domains to get the text for language model, and we translate this text to the parallel English. This we call monolingual. For evaluation, we use a data set called SCUA, which is a conversational data mainly dominated by Levantine dialect, and another data we collected specifically from different dialects and different domains to ensure during our evaluation that we're not biased to a specific domain or a specific dialect. So to assess the quality of the generated text, we ask bilinguals to rate the naturalness acceptability of the utterances from 1 to 5, very strange to perfectly natural, and whatever falls in this, the last 3 from not very natural to perfectly natural, we consider it as an acceptable code switching. So with subjective evaluation, we found that average mean opinions, based on the average mean opinion score, that the generated data with equivalence constraint was more accepted than the actual real code switching data. By looking carefully at those unaccepted segments, we found that most of them are incomplete sentences that has disfluences and a lot of repetition, sometimes overlap speech. Of course, the lexical replacement is the least accepted by humans. But does this really matter to improve the quality of the code switching for ASR downstream tasks? So we perform objective evaluation based on perplexity, and for acoustics, we used HMM-TDNN hybrid system, and we report the word error rate. So just as a reminder, the baseline is MGB2 and TDM3. The mono is everything that we collected as text from transcriptions, different dialects, different domains, and their translations. Just by adding this monolingual data without any code switching, we can see a large impact on the performance, both perplexity and the word error rate, around up to 22 relative reduction in perplexity and up to 5.4 reduction in word error rate. Then we add some generated code switching based on the linguistic theory with random replacements, or some with the random replacements, also with another one is with the morphological segmentation and the prior knowledge of number of switching points. And we can see we get some small improvement over that. However, as we improve the quality with better alignments, better segmentation, we can see that it only marginally shows any improvement on the model. Finally, we go to an extreme and try the just random lexical replacements, and surprisingly, we see a huge impact again, up to 35.7 relative reduction in perplexity and 2.7 relative reduction in word error rate. And we hypothesize that this is mainly because the random lexical replacement have more of the regularization impact on the language model. So the overall improvement is up to 65.5 relative gain in perplexity and 7.7 in word error rate. So the main takeaways from this part is morphological segmentation is crucial to obtain accurate alignments to synthesize a realistic code switching. However, improving the quality of code switching does not always improve the ASR performance. Random lexical replacements provided the largest gain for both language model and ASR. Next, I will hand this to Angie.
Thank you, Amir. So in my work, I would like to look more into whether we can improve lexical replacements by, instead of replacing at random positions, that we actually learn which positions are good candidates for code switching points and then replace accordingly. So next, please, Amir. So in summary, we created a code-switched Egyptian Arabic English parallel corpus. We use it to do the data augmentation, where we explore predicted versus random code-switched points, and then we evaluate. Next, please, Amir. For the data augmentation approach using the code switching predictive model, it goes as follows. So we fine-tune MBERT model using the 2.2 thousand code mixed parallel sentences that we gathered, such that given an English sentence, the model learns to predict which words are good candidates to insert into the corresponding Arabic source side. Next, please. And in the inference, what we do is we augment 300,000 monolingual parallel sentences where we provide the target side to the MBERT model, we obtain the code switching point prediction, and then we use the English words at those indices, reflect them into the Arabic side, while maintaining the order of consecutive English words just to handle syntactic divergence. Next, please, Amir. And for that, we investigate two types of alignment configurations, either using intersection alignments to do one-to-one word replacements as denoted by the X's, or we investigate the use of GROW-DIAC final symmetrized alignments to identify aligned segments and perform segment replacements accordingly. So in total, we have 4 variations, either making the replacements at random positions or predictive, rand versus pred, or using one-to-one word alignments versus segment alignments, which is one-to-one versus end-to-end, as we denoted. Next, please, Amir. Thank you. And now we have 3 research questions. First of all, can a model really learn to predict CS points given very limited amount of CS data? So in order to do that, we evaluate the output of the predictive model itself by comparing the predicted CS points to the actual CS points in ours in DevSat. And we understand that this is not a perfect evaluation because false positives are not necessarily incorrect. However, we do get an intuition on how well the model is performing, where we see improvement across all measures from predictive over the random. So we do think that, yes, it is learning something to some extent. Now, for the second research question, well, given that, does that mean that it can generate more natural synthetic CS data? And for that, we go for a human evaluation study. And here we're presenting the percentage of sentences annotated as quite to perfectly natural by human annotators. And we observe that for both alignment configurations, for word alignments in blue, for segment alignments in purple, we see that the predictive model gives us more natural synthetic data. However, yes, thank you, Amir. The third and most important question is, does it really matter? And for that, we evaluate on 3 extrinsic tasks: language modeling, speech recognition, and machine translation. Next, please, Amir. So in that case, we use a baseline that is trained on a small amount of code mixed sentences and large amount of monolingual sentences. And we see that the findings differ depending on alignment configurations and tasks. So when using word replacements using intersection alignments, we see that even though the predictive model generated less amount of data, it outperforms the random model on language modeling and machine translation, but not on speech recognition. Next, please. And now when we use GrowDiag final symmetrized alignments to improve the generation, we find that in that case, the whole quality of augmented data improves as reflected in perplexity and human evaluation. And in that case, the benefits of using a predictive model diminishes and random completely takes over. We believe that random has a very strong advantage that it is able to generate a wider variety of code switching styles that can be present in the test set, as opposed to the predictive model that is limited only by the amount of limited data that it is trained on. Next, please. And the best random approach achieves 45% improvement in perplexity, 4.7 on MT task for blue points, and 7.1 relative improvement for ASR. Next, please. So I would like to conclude this part of the presentation that we find that using linguistic constraints or a code switch predictive model for improving the lexical replacements, it actually generates more natural synthetic data as annotated by humans. However, we find that random lexical replacements outperforms both approaches for downstream tasks while providing a very simple and language agnostic technique. And now I hand over to Bara.
Hi everyone, my name is Bara. I'm a PhD student at IIT Bombay. So we also explored the generation of code switch text from pre-trained models. Can we have the next slide? I think we skipped one. Okay, fine. So we tried to explore the generation of synthetic code switch text from pre-trained models without hinging on any linguistic theories. So in the transfer learning setup, we have the scenario where we consider pre-trained multilingual models, which have been further exposed to monolingual text in the target languages participating in the code switching. So yeah, next slide. So for the generation of English-Arabic code switch text, we decided to engage BiBERT, which is a variant of XLMR, which has been further pre-trained on large amounts of monolingual text in Arabic and English. So before sampling outputs from BiBERT, we first fine-tune it on a limited amount of real Arabic English code switch text we are available. Next slide, please. Okay, so in order to derive code switched text from BiBERT, we feed in a monolingual Arabic sentence while masking a random word. While decoding at a position corresponding to a token position, we just add a simple constraint that the decoded word or the decoded token is English, and the decoded token is then substituted back into the same input and passed through the model again to decode the next token position, and this is repeated until all the token positions in the masked word are predicted. So this is how we do sequential sampling of the masked word within a bidirectional context and create code mixed data. Next slide. Here are a couple of examples where you can see the monolingual Arabic sentence and the corresponding code switched English-Arabic sentence that was generated through BiBERT. What's interesting about these generations, in contrast to other methods, is the fact that the replacements are not necessarily the translation of the original text. It can be anything that makes sense to the model based on bidirectional context. In fact, in the first example, you can see that the replacement is actually in conflict with the original Arabic text. Nonetheless, it is an equally acceptable code switched sentence. So this shows the potential of using pre-trained models, generating code switch text, which can be much more diverse compared to traditional methods, which only rely on translations or bilingual dictionary. Next slide. Yeah, so these are the results from the preliminary experiments we did for the evaluation of the generated code switch text. One is where, the first one is where we train n-gram models on the monolingual text in the two languages, augmented with synthetic text from BiBERT. And we can see huge reductions in perplexity over test corpus, which is taken from real English Arabic code switch text. Again, the second evaluation is where we rescore the lattices in an ASR system from an n-gram trained on the synthetic text. And we see some improvements in the word error rate with respect to a baseline, which has been compiled from some speech transcriptions. Next slide. Okay, on the text corpus that we use to compute the perplexity, we do a fine-grained analysis and we compute the average cross entropy across the bigrams, which have been divided into 4 different categories based on the language of the 2 words in the bigram, which can be Arabic and Arabic, Arabic and English, and so on. Across the bigrams, we see that the average cross entropy value for the n-gram model, which has been trained on the code switch text generated from Viber, has a lower value. Next slide. So following up on this, we can make the substitutions at the phrase level instead of the word level. And this is where we can also draw in from linguistic theories to choose appropriate phrases to switch to the other language. Also, we can explore constraint decoding and beam search at the entire sequence level without being restricted to words or even phrases. Again, human evaluation of the generated code switch text is another to-do. And we can also explore similar methods for language pairs other than beside English Arabic. That's it, and over to Jay and Brian. Thanks.
Hello everyone, my name is Jay and I'm a PhD student from University of Edinburgh. Brian and I have worked separately on code switching text generation, but we both make use of parallel data. So I will first introduce our architectures and share some high-level results, and Brian will take over and present the detailed analysis on the results. So I will briefly talk about our motivations here. So the first, similar to some works presented before us, is to leverage the large amount of parallel data. But different from them, we try to train a neural network to generate the code switching without any assumption of any specific linguistic theories or the existence of any NLP tool like parser or liner. Also inspired by this curious question whether code switching can emerge out of simple bilingual exposure, we explore whether pre-training on parallel but no code switching data can help output code switching sentences. So let's dive into the modeling. So this is a standard attention encoder-decoder model. So the input to the encoder is a parallel text pair, and the decoder, and we train the decoder to output code switch sentences. The parallel text here is just the civil Google translations of the code switch sentences. So the key component to this model is the attention mechanism. So each decoder time step produces a normalized attention weights over your encoder positions. That lets us define a weighted sum of your encoder hidden states. We call it context vector here, and the decoder hidden states and the context vector can determine your distribution of your the next word. Pointer generator networks has a slightly different attention mechanism. So this vocab distribution here is interpolated with your attention vectors. So that allows us to directly just copy the words from the input. So this is quite useful for code switching generation, as most of the words in your code switch sentences are present in your inputs already, and it is much easier to train the model to just learn to copy the words instead of modeling a more complicated word distribution. I will talk. So now that was pointer generator networks. I will talk more about another approach Brian has taken. So he aims to generate code switching without training any of them. So this is a standard encoder-decoder framework. So the input to the encoder is just one monolingual sentence, and we force the model to generate itself as well as the translation of it from the other language. Also, he found that conditioning on the output language by masking out the vocabulary of the other language helps the model to learn better representations. As the model has never seen any code switching data, decoding naively will lead to no code switching at all. So what he did is using this constrained beam search method. So where all the beams are collected into 6 beams, ranging from no code switch to 5 switches. So at each time step, the expanded sequence will be grouped into different beams, and each beam is proved separately during beam search. In that case, the code switching beams will not compete against monolingual beams. We also try to fine-tune the model on the code switching data and still see some improvement. So we are working on Mandarin and English code switching, and all experiments are conducted on the CME dataset. So we first translate the code switching part of the CME data to monolingual with Google Translator, then train our models on the translations, then use the model to generate some synthetic text. Then we train our n-gram models on the text, and in addition to perplexity, we also evaluate the performance when decoding using an ASR system. So broadly, that kind of give us 4 different data to compare. So we have baseline, which includes all the monolingual data, as well as the translations of your code switch sentences. And we have a pointer generator generated sentences, plus the monolingual data in your baseline, and also encoder-decoder framework generated sentences, plus the monolingual data. Also, we have a top line with the real CME code switching data, plus monolingual data. So here's the results we have. So you can see that the pointer generator networks and fine-tuned encoder-decoders marginally outperform our baseline. But if you split the depth set into code switching set and monolingual set, you can see the improvement is much clearer. So Brian will then explain the details.
Hi, I'm Brian. I'm a second-year PhD student here at Johns Hopkins, and I'll talk about some more results. So let's take a closer look at perplexity. Here we train separate n-gram language models on the different kinds of data, and we evaluate their perplexity on the CME depth set. So the models here all share the same vocabulary so that the perplexities are more comparable. They're not interpolated as in the previous systems, the systems in the previous slide, just for a simple comparison. And going from left to right, we have the real code switch text condition, and then we have the pointer generation networks outputs. We then have the encoder-decoder models, either fine-tuned or trained on only parallel data. And then finally, we have the monolingual sentences and the translations. So we break down the overall perplexity into by grouping sentences into monolingual ones and code switch ones. And as expected, the monolingual training leads to best monolingual perplexity, and training on real code switching data leads to the best code switching perplexity. The pointer generator and the fine-tuned encoder-decoder models are all supervised with the real CS text. So their generations, while not as quite as good as real CS, they're pretty close. The encoder-decoder trained on only parallel text does quite a bit worse, because during training it has not seen any code switching data. And although we can use constrained decoding to force it to code switch, it doesn't really track how the CME speakers switch. All the 3 methods just mentioned are content-wise only trained on the CS part of CME, and also they might suffer from some errors from the silver translations we obtain from Google Translate, and that might explain their poor performance on the monolingual part of the dev set. And finally, it's a curious surprise that we see that the monolingual model is actually doing decently well on the CS text, so we try to figure out why. So we note that although half of the sentences in the CME dev set contain code switching, but if you look at the word level breakdown, only 12% of the boundaries are actually switched. In other words, grouping at the sentence level in the previous slides might have overestimated the monolingual model's performance on CS text. Is this hypothesis true? So let's look at the next visualization. So over here, we break down the cross entropy by the token level direction of code switch. The cross entropy here is log base 2, so increasing the unit by 1 will lead to a double in perplexity. What we see here is there is a decent gap between the monolingual model in Cyan and the batch of models either trained on real or synthetic code switch text in terms of cross entropy, specifically on the code switch directions. And this gives us some confidence that our hypothesis might be right. So here we take another question is, the monolingual model still seems pretty strong. There is a gap, but we would expect it to be much worse because it doesn't have any code switching data. So next we take a deeper dive by breaking the cross entropy down further, and let me explain. So this is the same plot as before. And then these two plots show the distribution of n-grams, highest order n-grams that was used in backoff. And we also break the cross entropy down by that metric. So for example, the cyan bars in the middle plot show that the monolingual n-gram language model is backed off all the way to unigram 70% of the time because it doesn't have coverage of that much bigram and trigrams. Now you might ask, well, what's this 30% over here? The monolingual text shouldn't contain any code switching bigrams or trigrams. So it turns out that it's part of the artifacts of the Google translation that we did. So it was able to translate to pure English pretty well, but when it translates the code switch sentences back to Chinese, it still leaves some English text in there. So when we remove that and just use purely monolingual CME data, it backs off 90% to the unigram. The remaining 10% is from things like number words that could count as both English and Mandarin, but ended up counting as English, or discourse particles like and o. So the observation here is that the monolingual n-gram models and the code switch n-gram models are doing complementary things. The monolingual n-gram model has better unigram coverage in terms of the words of both languages, and the CS models have more coverage on bigram and trigram. They also have lower cross entropy when they are using their bigrams and trigrams. Okay, so let's now turn to the word error rate breakdown. So we're using a monolingually trained acoustic model to evaluate. So the language model's job is to model the switching points. In that, so in the same spirit as the perplexity evaluation, we would also like to focus on the code switching boundaries. So here we use a metric that finds all of the code switching boundaries and builds windows around them and evaluates word error rates on those windows. So as we extend the window size, we put more weight on the monolingual performance, and we will expect to see a smaller gap between our CS models and the baseline monolingual model. And overall, the pattern is similar to the perplexity results in that language models who have better code switching token level gains in perplexity leads to better gains in this window metric around CS points too. So to summarize, code switching data is expensive to get and scarce, so let's do data augmentation. We focus on the textual part and help improve the language model of downstream ASR systems. We train a generator using parallel data with or without code switching text to supervise. And then our analysis showed that the code switching and monolingual models are complementary, so we should interpolate them. So for future work, more immediately, we are thinking about trying pre-trained embeddings for both of our models because our models are trained on still relatively small sets of data. We would like to apply this to more languages. And then in the longer term, we would also like to relax the parallel input requirement for the pointer generator networks so that it can work with things like a single monolingual sentence and some phrases in the other language. So that's all I have, and I'll hand it over to Krithi for a final summary.
Thanks, Brian, and thanks again to all the students. So here are the key takeaways from this module. So regardless of the strategy that we adopt, augmenting with synthetically generated code switch text to train LMs yields consistent reductions in perplexity when tested on real code switch text. And monolingual code switch LMs have complementary properties, so it's a good idea to interpolate them. And we also saw that there were improvements that we got on downstream tasks from these LMs which were trained on synthetic text, so both ASR and MT. But that said, qualitative improvements in generated text as determined by a human, they need not always translate to improvements on downstream task performance, which we thought was an interesting observation. So with that, we'll wrap up here. Thanks again for listening, and we are open to questions.
Thanks, Pretty, and thanks for all the students who. We can take 10 minutes for questions before the coffee break. Okay, so we can take 10 minutes for questions. Yep, sure.
I was wondering, as one of the characterizations of code switching, it's not really human code switching, but imagine like a Swiss broadcaster that's going to switch among languages over the course of time. What would you call that, and would your approaches also lend themselves to that?
All right. So I'll just repeat the question. The question about what will be the situation for a code switching where a scenario like a Swiss in a country like Switzerland where people code switch. So I'll say my opinion, but maybe Pretty or others can participate into answering. What we try to avoid in this workshop is to make our own definition of code switching. And we did our best to collect lots and lots of data. So you may have seen by doing this effort, we realized there is in South Africa, people surprisingly switch between 5 languages. However, what you have described is a little bit closer to language diarization. And in our naive assumption, like 2 years ago, when we started to work on this, there was no clear definition. We started to glue sentences next to each other. So we take a sentence from the MGB2, glue to a sentence to Tedliam, and say, okay, this is what we think as a code switching is happening. Although at some point when we always remember this exercise, when we did the MGB3 challenge, I did grep minus V A to Z. So anything, this is noise. It didn't occur to our mind at that time that code switching is a phenomena that we should be looking at. But most of our study right now was where people are code switching on the level of 4 or 2 words per sentences, but not much of a change across the language. I don't know if Pretty, you have something to say about this.
Yeah, no, I echo what Ahmed said. And just one quick point, because the idea where we use multilingual pre-trained models, so those we could imagine could adapt to the setting where we have many languages as well. So that is something that we could experiment with. But it's a good test bed where we can try this out.
Yeah, sure.
Question. Problem sometimes is not so much switching language as switching scripts. And we can make a script and make it a Latin script at the same time. Some of the same techniques would work, and we had struggle with those issues.
All right. So the question about changing the script, not just changing the language, and how do we handle it differently using code switching or language diarization using the same script or different script? I'll say a few words, and then maybe Pretty or others can comment. So when we looked at the languages, we looked at 2 languages where 2 language pairs definitions where they share the same script, and this is something like Spanish English, Xhosa, Zulu English. Again, the script was the same. This is, in our view, is harder than languages where they have a different script, like Bengali English or Telugu English or Arabic English. So we looked at both of them, and perhaps when we come to the evaluation part, you will see how did we try to address and understand. Because what we found is just people make their own random choice of writing the script. So we looked, for example, at the inter-annotation agreement. The inter-annotation agreement in dialectal can be 70 to 80%, just inter-annotation agreement. But accepting the output from the system using different script can go to 20%. We just ask people to accept the output as it is. So the influence of the chosen script has a bigger impact on this, and we'll talk a little bit more when it comes to the textual representation. Yeah.
So in code switching, everything I've heard so far is across languages, but not necessarily across dialects. So an example I'll give you is as a Lebanese talking to an Egyptian, as a courtesy or cultural courtesy, I might pick up Egyptian words that are not native to Levantine or Lebanese Arabic, and vice versa. Have you looked at that?
That's a very interesting question. So initially, when we started to, I'm sorry. So the question about most of the work that has been presented so far is the code switching across languages. No much has been done across different dialects. So, for example, I could ask a word in Arabic, but when I say it when I say a word in Lebanese, it will be different than saying it in Arabic. Have we addressed this in our code switching challenge? So we did not precisely look at it, When we looked at Arabic, for example, the exercise that Amir has been doing, he looked at two corpus, the Isqua corpus and Canary corpus. The Isqua was a collection of 2 days meeting in the United Nations. And I'll tell you a very interesting thing happening. We found the system in one of the scenarios is the end-to-end ASR we built. The Lebanese dialect is often choosing the English script, while the Egyptian was choosing to write the Arabic script. That was very interesting. You know, it's a very interesting transformers. You put a lot of audio, a lot of transcription, and you assume that things will come good at the end. But when you look at the output, you cannot really quite clear what's happening. And one of the hypotheses, we thought, oh, okay, so the transformer learned that, you know, because there's a Lebanese dialect, I'll choose the English script, you know, I say, I'll go to Washington, or transformers, or information. This works. Can occur in both scripts. And what we found is just it can sometimes influence how native is your English. It's mainly the L1 and L2 rather than the dialect. So we try to generalize our findings across different dialects. The second thing, which could be really challenging when you talk about things like dialectal Arabic, the dialect doesn't live by itself. I mean, like what we have learned so far, when you talk about Lebanese Arabic, perhaps you talk about 60% MSA or maybe 50% MSA, 50%. When you talk about North African or Algerian, you expect 10% MSA and 90%. So the dialect doesn't live by itself. One thing we have been missing, and we haven't gone that far when we consider dialects, given that we don't have different script, we were not able to go that far in differentiating between the dialect. But we generalize our findings using the corpus that has multi-dialect similar to the work that Amir has done. Yeah, sure. Go ahead.
Right. So to me, you have two contradictory conclusions. One side, you said when you do the data augmentation for code switching, by introducing the constraint from the implicit by leveraging those behavior of the code switching from real data and generating the augmented code switch data, and ask human to do the most score, and it turns out to be more natural than random replacement. On the other side, you say you do the random data augmentation and you get better whatever rate. And look at your way you do the ASR, and left side mentioned you use an environmental model. I was wondering, is that possible that environmental model is not the best tool in this case for code switching, because think about the scenario, say open A app, A is in Arabic, and open B app, and B is in other languages. And if you do the environment modeling, say you modeling the transition probability from open followed by A and open followed by B, but those patterns we'll never see in the test data, right? So if you're modeling using environment, it's very easy to have the overfitting problem for the training data which you never see in the test, which makes sense that you should switch into iron language model or using the class language model. So you group A and B together as a class, and then you model the open and to something terminology and of class. And inside that class, introducing the uniform language model from other languages. Would that be a better solution than just look at the background or environmental model?
That's a very good question. Amir, do you want to talk about it? Because that's part of the experiment. You have this finding, but I repeat the question to the audience. So basically, the question is just we have contradicting results. At some point, we're saying that the language model is helping us, but the human performance is better. And by saying the language model, is it a limitation? Is because in the n-gram, and potentially we could solve this by using some techniques in the neural language model, such as having a class base where we point where the code switching is happening.
Yeah, so I would like to first clarify that the task that we had is a new domain code switching. So we assume that we don't have any access to this code switching data, which is a realistic scenario because you will never have something that covers every kind from different dialects, from different topics of code switching. So in that sense, randomness helped more. We might expect that if you have something from a specific domain, like a part of the data that you collected, what you expect, and maybe you train the model on that, that might be more competitive or better than just random replacements. The other thing you mentioned during doing something like neural networks, we tried actually LSTMs, and it gave us the same conclusion, but with slightly worse results. So we think that maybe in this case scenario, n-grams is easy, like it's breaking the constraint, like breaking the long sequence dependencies, because in general in code switching, you need a lot of data to learn some kind of long sequence dependency on the same word, like how many times you will see the same exactly word in the same context. So usually you back off from n-gram models, from trigram to bigram to unigram, just using the vocabulary that you have. So in that sense, we had the n-grams performs better, and in this scenario for zero-shot learning, random replacement is better.
Just make sure I understand correctly. So when you say you did try using iron length model or using other technology to do the ASR when you could code switching test. So can you be more specific? Are you doing using the original ASR system with n-gram model, dialectal index, and the multi-model rescoring, or did you use RNT, which explicitly modeling the model? Which way did you do?
I just used rescoring, LM rescoring, not RNT.
So until this moment, so far all what you have heard is not doing anything with the acoustic model or during the decoding, assuming we get the ASR output and we try to benefit from the language model. And for the language model, we looked at two hypotheses: as using the n-gram, or in some experiment we use the RNN or the neural language model. But also at this stage, I'd like to highlight a couple of important facts. A, we try to generate code switching using some linguistic rules, where we did subjective evaluation, human like it more than what they see in real scenario. Although when we put it in the machine to rescore the output, we don't see that huge gain. And our intuition at this stage is two things. Is A, the text that we like is different than what we speak, because when we speak, when we hesitate, we mumble, we do lots of pattern things we don't understand as the current linguistic intuition that we have been using. Secondly, which is more important, we are reporting word error rate, and at the second part of the discussion, we will highlight that word rate is not really a robust measure. I mean, if we would had enough time, we would have propagate our new evaluation metric on all the work that we have been doing at this stage.
So this question maybe complements Michael's question about switching in scripts in the written form. So I'm interested in changes in phonetics in the spoken form. Now, maybe in this workshop you just talked about mainly about the language models, but there's certainly a difference. I'm not a Spanish speaker. If I ask about the recipe for empanadas in Mexico, those are loan words. I'm not saying them with a Spanish accent. I'm not really code switching. But somebody else might ask about the recipe for empanadas in Mexico. I can't say that. I don't really have the accent. But they're code switching. In fact, maybe ostentatiously in order to show that they speak Spanish. If you're doing text-to-speech or speech-to-text, should we be modeling the changes in the phonetic realization, in the phoneme inventory, the contextual phonetic realization, in order to get better ASR performance and better text-to-speech? And do you, in the corpora that you have, do you actually see a difference between, say, loanwords and code switching? In the Hindi example, I can't actually tell whether that person is code switching or they just don't know a word for crystal in Hindi.
Cool. So,
that basically just
I can repeat the question, then Matthew perhaps have something to say about it. So the question was, we considered languages where we have changed across script or within the same script. Have we done any work to consider the phonetics or the phoneme pronunciation? So maybe somebody will say something where the language is not a native speaker and the differentiation will be mainly in the phonemes. And of course, this matters a lot to the text-to-speech, because when text-to-speech, we care a lot about the accent and the dialect. And in our ears, we pay attention. Have we considered this in the ASR? So Matthew, do you want to say something?
Maybe I think we touch upon it at least a little in the next round of talks. So bug us again if you are still unsatisfied, and we'll try to clear it up.
Sorry to jump in.
No, that's fine.
Which is me the question in the right time.
I actually what was said is a very beginning of the presentation. Code switching is very viable, and maybe it's more accurate to say that the switching and all that than in the case of multilingual, that Because at the end of the spectrum, someone that is switching completely phonetically, so it's, I think it's very diffuse, and there are many ways of doing code switching and the function of regions and
Yeah, I was wondering about this with respect to the metrics also. Okay.
You are asking on exactly the coming slides. You are just in the right track. So lunch break is, the coffee break is holding you from getting all the answers.
One last question, following what Jason is asking. So what happens, for example, if you have a word that is half, let's say, English and half Spanish? How do you count that one?
Give us an example.
Like, yeah, like taking an English word and like
Because we have an example for you from our data. We have the word international in Arabic or in English, where thanks to the word pieces, the encoder decoder managed to get enter in Arabic and national in English, and they glue them together. And we have a script with this as an output. And when we looked at this, we didn't know what to do.
That's maybe just a choice in representation. Paula is really thinking about a word that's originally in one language, but something which added to it from the other language.
So a good example is an Arabic word, and then it's or an English word conjugated in Arabic. And a diskette. We're talking about a disk, but now the plural, and
Right.
you're talking about the, the disks. El diskette. One word.
Right.
Starts with Arabic, middle is English, ends with Arabic.
Yeah, for example, now the teenagers in Mexico, they say in socialization or something like that, to mean that they are going to hang out with somebody, right? But the social is like kind of English, but then the ending is like English, so it's kind of code switching.
So one way to think about it, if you go back to the dialect identification, we have been asked, what's the dialect identification? How did you do this? And the best answer is that dialect doesn't know boundaries. Dialect travels, right? I mean, we say, oh, Gaelic here, Spanish here, Portuguese is here, Egyptian is here, but dialect doesn't know this. So if we take the same way to generalize it into the code switching, I mean, the best example when somebody was saying, this problem is sophisticated. I mean, she's Arabic, she was speaking Arabic, but she tried to understand the word sophisticated, and she said, the problem is not sophisticated, it's sophisticated, because the so is just, S-O space sophisticated. And then blah, 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 Arabic sophisticated. What's sophisticated? But if somebody thought through about the word, and instead of adding prefix to the word, he removed some part of the English word. So we see all these kind of things, and we have not made any proposal on how to handle this. We are mainly at this stage driven by the data.
So a follow-up thing, what happens with those small words like okay, so are they English?
Is okay an Arabic word?
Well, Washington is an Arabic word. So, okay, it's very, very Arabic word. Again, we are data driven at this stage. Most of the time, we are influenced by what we see, and we have lots of things that's written in multiple languages, and we address this on the language model and on the evaluation, and it's a real challenge. All what we can tell you at this stage, we became more and more aware of this rather than propose a solution. And in the last slide, maybe we'll have a collective effort to address this. Can we take one more question before the break? Okay, one more question then, because we put once.
So thank you for the presentation. My question was on like the data augmentation as well as the predicting the code switch points part. So just asking, especially with the examples that Vector started, do you see that the frequency of the given token in the monolingual corpus for the source language, if that can be a signal or a predictor for like a switch in the target language in the code switch sentence? So like with the example in the Hindi sentence, for example, the terms that were code switch were essentially Romo, Hetero, Cuban, Crystal. Even as a human being, as a native Hindi speaker, I would not know these terms. So I would, in a naturally occurring code switching corpus, I would exist these terms to be code switched because I would use the more dominant language or the language that I'm more familiar with to use these terms. So have you perhaps used them as a naive signal to detect code switching points, like a token that's very rare in the source language vocabulary?
Okay, so I'll repeat the question and maybe Pretty can help to answer this. So have we looked at any signals from the monolingual where the code switching is happening? So for example, we can have a specific word in the Hindi word that, it is giving us a clue for what code switching word could happen after this. Have we looked at something simple like this in a scenario where it's a simple and quick and easy way for linguistic rules to generate code switching text?
So not specifically during the workshop, but we did look at like part of speech tags and also a frequency of tokens as an indicator of code switching points. But I think maybe Inji will want to comment because she did explicitly look at predicting code switching points. So Inji, were there any cues, especially kind of frequency related cues?
So again, like in previous study, we also saw that POS tags, and that was seen on multiple language pairs. It's a very good cue for that. In our study, what we found is that like the only thing that related in this question is that we tried to check the correlation between the POS tags, between the predictive model and the random model against the actual POS tags of code switched words. And we found that the predictive model gives a higher correlation of POS tags when compared to the actual CS words as opposed to the random model. But then it's the normal distribution that everyone really reported, like nouns dominating, followed by verbs, and then other POS with very slight percentages. And the nouns could go up to 80 something, 90 something. So it's really dominating.
Right.
So that's input here.
Okay. So if there's no more burning questions, we thank our colleagues in the understanding and the text generation. We'll take a 10 minutes break and see that. So the question from Ken, is there an inclusions of gender self-identity in code switching? Is this more prevalent of some gender identity than others? So I would come. You can sit here closer. So Ken, if you are online, I will call my colleague Electra to answer your question.
Jason, Nancy.
I just go.
Yeah, go ahead.
Yeah. So the literature. Okay. Yes. So the question is there an influence of gender self-identity on code switching, and is this more prevalent for some gender identities, I guess, more than others? So Danny did actually talk about this a bit. She introduced the fact that gender is a higher level variable that might influence the type of code switching we're going to see. Her results weren't particularly significant, but I can talk about what the literature says. And there have been studies to show that gender does really significantly affect code switching and code switching style. It's partly culturally dependent. So in some places, in some communities, we're going to see men code switching more, potentially because we have links to things like confidence or informality. Code switching is generally seen as more informal. So there are possible situations where women might feel like they can't be informal in situations. But then I think in other communities, women are known to code switch more. So this potentially happens. Well, more generally within linguistics, there are studies that show that women lead language change. So women tend to pick up on changes and start to make changes in speech faster than men. And so if we're thinking about code switching in terms of the mixing of new languages into an existing language, then in those situations, women might code switch more. So the answer is it can have an effect, but the effect it has varies from like society to society.
Hi, so I'm Matthew Wisner. I'm at the Human Language Technology Center of Excellence over here at JHU, and I'm going to talk to you about ASR specifically. So we used ASR before as an evaluation tool for language models, but here we're going to be actually developing ASR systems specifically for code switching. And this is something that many colleagues worked on. So all the way from University of Edinburgh, Andre, Preeti at INT Bombay, Luca Ondel and Léa-Marie at LIMSI, here at JHU, QCRI, collaborator from Unifor, and obviously CMU. And all of these people will talk to you about various techniques we explored for improving ASR and code switch scenarios. So in general, in speech recognition, we assume that we have speech from a person speaking one language. We have transcripts from that person, and we can use this speech into some system that we're going to train along with these transcripts to train a nice system. All right, so at test time, we are hopefully fortunate enough to have a person who is speaking the same language, and it's a match test condition, and things are nice and things work well. What's challenging about the multilingual and code switching scenario is we're assuming that we have monolingual data to build ASR for code switch systems. And this is in possibly multiple languages, but at test time, we have a very big mismatch. So here we might have speech in multiple languages, it might be switching within the same utterance, and we need to build some sort of ASR system that's capable of handling both of these things. So more generally, we want to switch from this purely monolingual modeling of speech into a bilingual and even multilingual modeling of speech. And there are really a few different cases of this. So we want to be able to handle monolingual cases of both languages, and we also want to be able to handle code-switched cases of speech. But these come with very different data resources. So in general, we can assume that we have copious amounts of monolingual data, at least in many languages in the world where we see code switching, but a relatively smaller amount of code switch data. And we're going to denote these throughout a lot of these presentations with these symbols above. So XCS refers to code switching, XL1 is the audio in one language, Y is the text in another language. Okay. One case that we really care about is when we don't have access to any audio data that is code switched. So we're going to assume that we have some text that is code switched, and the last presentation showed how we can generate this when we don't have it. So this is somewhat of a realistic assumption. We might not have this text at all. Again, we can generate it. But what if there's neither? So one thing we'll look at is how we can also create synthetic code switched audio. And that's something that Dorsa is going to present to you about. So highlights of what we're going to talk about. Dorsa Zainali is going to talk about building synthetic code switch speech, this XCS here. Preeti and Ravi are going to speak to you about how you can generate sort of synthetic but really cleaned up code switch text by transliteration. Brian Yan and I will talk to you about some code switch modeling decisions that improve code switching ASR. Léa-Marie is going to speak to you about how you can use self-supervised models to improve code switched ASR in scenarios where we have very small amounts of labeled code switched ASR data. Luca Ondel is going to talk to you about how we can span the whole range of multilingual and code switch decoding using a new framework for lightweight and efficient multilingual decoding. And Andre Kleich is going to talk to you about a tool that he's developed for identifying code switch errors that really helped us in development of these systems. And it's an interesting tool. So, all right, thank you. Dorsa.
So hi everyone, my name is Dorsa Zainali and I'm a fourth year undergraduate at Carnegie Mellon University. And I'm going to be talking about building ASR system from generated synthetic code switch audio. So basically to motivate this, we don't have a lot of code switch speech, and also end-to-end ASR models trained on monolingual data don't really work well on code switch speech. And this is especially true for encoder-decoder models because they learn an implicit monolingual language model during training. So to alleviate this problem, we propose something called speech collage, which is basically using concatenative synthesis with monolingual data to construct synthetic code switch audio examples. So there's actually been a lot of work done on data augmentation with concatenative like synthesis and also for code switch speech recognition, but I'm going to be talking about two previous works that are kind of our motivator for our approach. So basically the first paper from Microsoft was working on domain transfer, and what they did was they had some underlying text in the target domain, and they took random segments from the training data corresponding to this text and concatenated them together to create new audio examples. And this gave them really good results in word error reduction, and especially better results compared with using TTS to generate these audio examples. And so basically they hypothesized, which we think also, that random splicing could cover more speaker and also environmental variability. And one thing where this kind of splicing was applied to code switching was this paper, where they basically took existing code switch utterances from the same speaker, and they spliced different parts of it together to create a new code switch utterance from the same speaker, and they added that to their training data, and they actually got good results with this. So, but these is our motivator. I'm going to be introducing speech collage. So basically, this example is going to be for the Mandarin and English language part, because that's what we focused on for our experiments. But so we assume that we have a English corpus and also a Mandarin corpus. And we also assume the existence of some real code switch text. And so all these three together, we have a real code switch text sentence, which we segment into units. And we basically take segments from these monolingual corpora corresponding to these units based on some criteria, and we just kind of append them together to create a new code switch example. Yeah, so basically, as you can see, there will be many ways to generate the speech collage based on different criteria and different unit sizes. So what we mainly focused on in our experiments was with unigrams, but we also wanted to know if it helps ASR performance if we use different unit lengths. So our tool, speech collage, also supports taking bigrams and also the longest possible substring that you can take from the monolingual corpora. And also so basically speech collage can cover a wide range of speaker variability and also speech quality. So we wanted to know, instead of taking random segments, would it help our ASR performance if we make the audio a little bit smoother? So in our experiments, we focused on basically creating a synthetic example that's kind of matched on energy. But you can also extend this tool for pitch and also other speaker features. So basically, I have three examples for you here. So the first two, well, I'll just go one by one. So the first one was with unigrams, and the first word or the first unigram was taken randomly, and then for the following ones, we kind of searched through our corpora to find one that matches the energy of the first one kind of closely. So I can play this example.
Accounting.
Right. It was kind of okay. I don't know. And then the second one, what we did was, still with unigrams, what we did was we took random segments for all of the words, and we normalized them to unit energy and then scaled them up to some randomly sampled energy. And yeah, I can play this also.
On demand.
Yeah, and then the third one lastly was taken with bigrams, but the same strategy as the first one, where we kind of search for an audio example that matches the energy of the first one.
Broadband.
Yeah. Maybe you can hear a difference, maybe not, but they're kind of more or less, I guess, the same. Yeah, so we generated about 50 hours of this synthetic code switch data, and we had three different models that we trained on. So the first row is training a hybrid model and two end-to-end models using only monolingual data and tested on code switch data. So I guess this would be the baseline. And then the second row was training with monolingual data plus the 50 hours of the fake synthetic code switch data. And as you can see, there was no gain in the hybrid model performance. And these are all word error rates, by the way. But there was a gain. There was a decent amount of gain for the end-to-end model performance. And the third row is training on monolingual data with actual code switch audio. And this would be the top line. And yeah, as you can see, it's a lot better, but we gain an improvement with our fake code switch audio. And yeah, so to summarize our work, we showed that speech collage actually does improve the performance of end-to-end models like we suspected, but it doesn't change the performance of hybrid models. And so for our future work, we actually want to release this tool for others to use for on-the-fly data augmentation. And also we want to explore, would there be benefits if we make the audio a little bit even more smoother, add more speech quality, but not as good, I guess, as the speech quality for gain given by TTS. So yeah, that is all I have for you guys. And I think Preeti is going to talk about generating synthetic code switch text next. Thank you.
Thanks, Dosa. Matthew, could I request you to change the slides? Or Ahmed? Yeah. Thanks. Hi, everyone. So I'll talk a little about generating synthetic code switch text using transliteration. I think there was a question raised earlier about script mismatch. So I'll be presenting on behalf of Ravi. So here our investigation was mostly motivated by the observation that many of the code switch ASR errors were due to script mismatch issues. So here's an example to illustrate this. The first sentence is a reference transcript of an utterance in Telugu English. The second sentence is exactly the same reference, but with the Telugu words transliterated. The third sentence is the prediction from the ASR system, where the errors are highlighted in red and green, except the green words are exactly the words company, launch, and official, but rendered in the Telugu script. So even though this ASR prediction would contribute 7 errors overall to the final WR numbers, it ideally should have been 4 if we were able to fix the script issues. So the question of whether WR itself is a good metric is a broader one, which will be examined in much more detail towards the end of the project presentation. But what we wanted to look at was whether we could use some simple script normalization techniques during AM and LM training to mitigate such errors to a large extent. So here's the text normalization scheme that we adopted. Next slide, please. So we just considered a text corpus of monolingual Telugu sentences and then went through each word in every Telugu sentence, transliterated each word, checked whether the English word form exists in an English lexicon. If it did, we replaced the word with the English counterpart. And the Telugu sentences which didn't have any replacements were ignored. So we were left with a subset of sentences, which we denote here by script YCS, which is now code switched. And we also have corresponding Telugu monolingual audio. Next slide, please. So our experiments used monolingual Telugu data, monolingual English, and small amounts of real code switched Telugu English speech. Next slide, please. So here are first set of results. Sorry, so before that, the ASR model itself. So we used a CNN, TDNN based hybrid model. Next slide, please. Which was trained only on the monolingual Telugu and monolingual English corpora. And the script-wise CS code switch, synthetic code switch text that we constructed were based off of training transcripts of monolingual Telugu speech. And so we ended up with 13K such sentences, which were additionally used both for acoustic model fine-tuning and language model interpolation. Next slide, please. So here are first set of results. So if you only use monolingual data to train the acoustic model and the language model, we see a fairly high word error rate of 56.58. Now, if we use the script-wise CS to further fine-tune the LM, there's a small reduction in WR and a larger reduction in WR if we use the script-wise CS to fine-tune the acoustic model. So what this suggests is that in the absence of any real code switch data, such synthetically constructed subsets of even the monolingual speech could be advantageous and mitigate some of these script errors. Next slide, please. So then we took a little bit of the real code switch text and augmented the language model training data to further rescore the lattices with a newly trained language model on the union of script YCS and YCS. And we see a large reduction. And next slide, when we use the real code switch speech also to fine-tune the acoustic model, we see an even larger WR reduction. So the final WR we end up with is 36.06. So here, a lot of this can be attributed to the real code switch speech being in domain and similar to the domain which was used in the test utterances. And some of it can also be attributed to the code switch errors being mitigated. But here, a point is when we add script-wise CS to fine-tune the acoustic model on top of the real small amounts of real code switch text, it does not yield any additional benefits. So in the presence of real code switch speech, adding these synthetic constructions to fine-tune the acoustic model may not be very beneficial. And finally, we looked at whether the script-wise CS, when augmented with the real code switch text to just train the language model and interpolate further with the best acoustic model we had, does that give us any benefits? And we did see a significant WR reduction. So these are some initial promising results, but there are many next steps that we can explore. So one is, can we just scale this up to much larger amounts of monolingual Telugu text? Can we be selective about how we do these English word replacements and only do it, say, if it exceeds a certain and then a broader question, of course, is whether these benefits will translate to other languages and also to end-to-end ASR architectures. So thanks everyone for listening. I'll now hand it over to Brian, who will talk about code switch modeling.
So when we're building ASR models, it's important to remember that code switching is a subset of general bilingualism. So if you're saying that you want your ASR models to do well on a interest-intentionally code switched set, you're probably also going to expect that these models need to encounter and deal well with purely monolingual Mandarin, for instance, and monolingual English. And as Matthew mentioned, we need to build these models under the slightly challenging data environment where we can have relatively lots of these monolingual ASR training data, but we might not have any code switch ASR data, or maybe we just have some textual code switch data. So to that end, it's useful to think about jointly modeling the monolingual and code switch ASR tasks. As a starting point, we can think about just directly doing this all together using bilingual modules that should just handle speech and text, regardless of if it's Mandarin only, English only, or code switch. And what we can do in this first approach is we can use an external language model to handle the output dependency. And we can train this using the code switch textual data that we might have. And then we can handle the acoustic modeling portion using something like a CTC framework where we're actually conditionally independent about the output. And so we can use this setup to generalize better from the monolingual ASR training setup setting to the code switch test setting. But we can do more. So we can start to think about the acoustic modeling portion where on the left, it's just modeling Z given X as having multiple parts. So we can use a conditional factorization to change from a bilingual CTC on the left side to a factorized version on the right, where now we're introducing these monolingual experts in English and Mandarin, shown in the blue and the red there. And so now we're modeling the Mandarin ZM and the English ZE given X, and then we're modeling the bilingual task as predicting Z given the ZM and ZE. So what we've done here still applies for the same training data. And now, by just doing this factorization, we've created these dedicated monolingual subcomponents. So we think that this will give you more data efficiency since we have these separate monolingual modules. And importantly, we've also reframed the bilingual task. So now we're just trying to predict Z given ZM and ZE, which just boils down to choosing the right language for every ZI given the monolingual information. So to jointly train, we just want to apply a training scheme where we can interpolate between three losses, the bilingual loss and the two monolingual losses. And so what we need to do is we need to have for any sort of speech, which could be an English speech XE or Mandarin speech XM, we need to give some targets for the opposite language. So on the English side, we're just asking the Mandarin module to produce these null tokens and vice versa on the other side. So this also applies if you have a code switch speech. You can obviously just mask out the opposite language portion. And so if we do this, what happens during inference is that we're asking the monolingual CTC modules to transcribe just their respective parts. And then the bilingual CTC module can then transcribe the whole, given those monolingual information. And then all three of those modules, plus an external LM, can all be jointly considered in a decoding. So at this point, it's important to think about what we're really asking the monolingual modules to do. So if you're going to recognize code switch speech in this framework, you're going to need to, at some point, decide which language is being spoken at what point in time. And in this framework, we're actually asking the monolingual modules to do that. So they're trying to make a language segmentation decision. They do so by producing these null tokens. So they're basically ignoring the other language. And we're asking them to do so in isolation and then pass that information on. But is there another way to do this? Can we do this at a later stage in the model? Can we use the bilingual portions of the model to look at both the monolingual inputs and then make this decision? And then can we use the external language model to also help us make this decision? So a way to do this is to, instead of asking the monolingual modules to explicitly ignore by producing this null token, let's actually encourage them to try and transcribe the opposite language. So we just need to make a small change to our training scheme. Everything is the same except for the opposite language target. So when we have an English speech, instead of asking it to produce those null tokens, let's ask it to produce some pseudo transliteration of the English speech. So this word accounting, we can run the speech through a Mandarin ASR model, and it's going to want to say something like cow ding, I think is what that says. And the other side, the speech, hi yo, let's ask the English model to say how you. So if we do so, now we're going to pass no language segmentation decisions anymore. We're just going to try and produce these pseudo transliterations at the monolingual stages. So now we've pushed the language segmentation decision further down, and we're going to consider both sides in doing so now. Okay, so now that I've talked about this language segmentation portion, which we think is very important, I just want to show you some examples qualitatively where you can see what's going on here. So this is a model trained with the early segmentation way where we're trying to ask the monolingual modules to ignore the other side. And here I've used code switch supervision, and these models actually work really well. So you can see in the red and blue there, the monolingual modules are doing well at knowing when it's the opposite language. And so they actually agree on which side is being spoken. But if I don't have the code switch supervision, this task becomes harder. So you can see the same utterance here. Now, we're still expecting that the model can produce the null tokens, but they don't in those cases in the red circles. And so there's no agreement on which language is being spoken. And I think some people in the audience were asking about cases where languages are very similar or dialectical. And I think my suspicion is that when we're dealing with those cases, language segmentation is definitely harder, and you'll likely see a lot of this going on. So conversely, when we move to the later decision, where we don't try to produce the null tokens anymore, you can see that instead the monolingual modules are just trying to transcribe the other language, and they're producing very smooth likelihoods for what's being said. Like you can see in the last word there, the you is very smooth. And so there's still some language separation information implicit in this smoothness, but the decision is much softer now. And so the LM can consider all these inputs and help us decide which language is being spoken at what point in time. Okay, so here's some numbers. The top section is the top line where we use all the available code switch data. And so when we remove the very useful code switch ASR data, you can see there's a pretty big degradation, 13 mixed error rate. But when we just shift the decision point about language segmentation to the later point of the model, we can recover a good amount of that, about 5 miserror rate. Okay, so before I hand it back to Matthew, some takeaways from this work are that language segmentation of code switch speech is definitely hard, especially if you don't have code switch supervision. And we found that making later decisions about language segmentation, for instance, letting us incorporate external language models to help is definitely very helpful as well.
So Brian showed how in conditional models, delaying this decision about language segmentation allows us to incorporate more external knowledge and helps us switch languages in a more realistic way, alleviating the training and testing mismatch that I described at the very beginning. For analysis, I'm also going to show you how we could do this in direct models. So this is maybe a slightly new technique, but it's also for analysis of what's going on. So recall that the direct model here, we had an encoder phi that outputs phi of x. And we finally have an output layer. Here it's a times phi of x, which is responsible for producing scores for each output unit that we have. So if you think about what's going on here, implicitly, the encoder phi and this output layer a, they have to implicitly make segmentation decisions about language. And as we mentioned, this is subject to training and test mismatch. And we don't actually know where in the model this language decision is being made. For all we know, it's actually very early in the lowest layers of phi. But we just said we want to delay this decision as late as possible so we incorporate additional information such as the code switch language model. So what if we could factor out the phonetic and language decisions that are implicitly being made by the model so that we have some control over these? And also it might help us analyze what's actually going on in the network. So consider this output Z, and it's outputting tokens Z1 through Zn, and each of them lives in some vocabulary. So this might be a practical system, but it's also for analysis. We're going to consider building the system with units that are shared in some way across language. So this might be phonemes, but you can imagine using characters if it were 2 languages in the Roman script. So each of these shared units, base units or phonemes, they also have language tags associated with them. So our output vocabulary is going to be number of base units by number of languages. And now we can actually factor our output layer into these 2 terms. So we have a term corresponding to phonemes P and a term corresponding to language L. P and L are fixed. They're just one-hot encodings of the phoneme assignment to the output unit or the language assignment to the output unit. And U and V are learnable. Okay, V is just a language embedding matrix, if you want to think about it that way, and U is a phoneme embedding matrix. Okay, and again, P, it's just this one-hot encoding matrix. So really, when we're making our output predictions for Z, there's 2 terms. There's a phoneme prediction term and a language prediction term. Okay. And this language segmentation term is the important part. It's latently performing some sort of frame level language segmentation. All right, so this is implicitly happening in our models, but now we can explicitly control for it and examine what's happening inside our models. So we trained on monolingual examples of English and Mandarin. And here is one such monolingual example. You can see the text of it on the top. In orange is the score produced by the language ID portion only. So this is only the language ID term. And you can see the score for English is higher than the score for Mandarin, shown in blue, okay, across the whole utterance. And this makes sense. It's an English utterance. We saw this during train. Okay, we can check a Mandarin utterance. And we see that it performs exactly as we think. So the Mandarin text is written on top. You can see that that is indeed a Mandarin utterance. And the score for Mandarin is higher than the score for English. This is doing language ID implicitly. All right, now this would be going on normally, even if you didn't have a factored representation. It's just hard to disentangle the difference between phoneme estimation and language estimation. But what happens at test time now when we have a code switched utterance? Well, we have a code switched utterance, so you can see on the top of the plot there. And in spite of the fact that it's switched, the language ID component is incapable of switching. Why? Well, we've trained only on monolingual instances. And you can think about the language ID task as trying to predict language from the input, but it also can use the full context of the input. It's only seen monolingual examples, so it will output exactly a monolingual language ID score for the whole utterance. And this is clearly not what we want in a code switch scenario. But fortunately, we actually factored the representation. So we have some control over this. So the hypothesis is if we just remove this mismatch component, we should do better. And lo and behold, removing this component actually reduces the word array by 2%. And in an updated version of this experiment, it actually, we pre-trained on larger amounts of monolingual data from mismatched domains where the accents might be different, for instance. And there the word error rate actually went down all the way to 34%. So I think what this indicates is that removing this implicit decision about language segmentation when you have this mismatch condition is very useful, and delaying the decision till later is, and using the code switch language model to make these decisions ultimately is helpful. So making later decisions about language segmentation is also better in the direct model, not just the conditional model. And here we enable this by using a factored output linear layer. So in the future, we really should try this for new language pairs, Xhosa English, Arabic English, and Telugu English, where maybe in these code switching instances, there may be very different ways of pronouncing words depending on the language they're in, or maybe the accent stays more or less the same throughout the whole thing. And this is the kind of thing that would be encoded in this term LVX. So I don't know if this is addressing your question at all. Maybe you'll have more questions later, Jason. But okay. Will this scale to 3 or more languages? So with this factored output representation, we might be able to scale this fairly easily to new, larger amounts of languages. And then maybe we can account for new domains, dialects, and accents by adapting only this language ID term, LVX. All right, so thank you very much. I'm going to pass this on to Léa Marie, who's going to talk to you about how you can use self-supervised models for code switch ASR.
Okay, so I'm Léa Marie from the Listen and the CAPIA. So actually I talked yesterday, so I will present pretty much the same thing, but in a shorter manner. So basically during the workshop, we wanted to study the SSL models and how we could use it for the code switching data. And so our data is this one, and so it's SOP or SOP hours data. We have 15 hours of labeled data and about 200 hours of unlabeled data, and some monolingual text. So here are some examples which I won't play, but you can see that code switching really depends on the pair. And so for the workshop, we wanted to address several things. So the first one was how we can use the SSL model. So we ran some experiments with so some TTC loss, but it was not good. So that's why we decided to go with using the SSL models to extract features and then use it in as features in an linguistic model instead of using the standard MFCC features. And we always use the label data. And so we found that the best kind of features that we can have with SSL models for our particular case of code switching is with the CLSR SSL model, which was trained on multiple data, so multilingual data. And then we wanted to address the questions of how or which kind of post-trained model we can use. So here, the MFCC MGB model is also a post-trained model, but it's not an SSL model. It was trained on only labeled data from English, so the MGB data, which is British English BBC. And then we use all of the 15 hours of labeled data from the soap operas dataset to continue some supervised training on this model. And then you have the XLSR model, which was used to extract features. So it's the same result as yesterday. So you have the baseline with the MFCC features, and then the acoustic model is actually trained from scratch. And then you also have the post-trained model. So the MFCC MGB model is using MFCC features, but post-trained on the English data. And when you train again on the labeled soap operas data, it's actually better than MFCC features. So no surprise here. But then when you use the XLSR model to extract features, it turns out that, surprisingly or not, this model is actually better than using the most common approaches. And for every cases. So the conclusion is that for the code switching data, when you don't have many hours, you can use some features from the SSL models. And most of the time, for us, it's better to use the features from the XLSR model rather than using FCC features. And also, we can use a pre-trained unsupervised model instead of using some supervised pre-trained model. And then the next question would be, since we have some unlabeled data, what can we do with that? And so the most obvious thing would be to use a post-trained SSL model to adapt it and run the pipeline to extract features. And then again, with the new acoustic model, try to use some semi-supervised learning. Now we'll let Luca talk about decoding and code switching.
Hello everyone, so I'm Luca Ondel. I am from Soon Listen Like Memory, and I will talk about multilingual, the design actually of multilingual decoder that are on one hand lightweight, that don't use too much memory, and that are also efficient and parallelizable on GPU. So the problem I'm trying to solve here is scalability. If you try to build a multilingual code switching ASR and you don't want just to go for 2 languages, but 3, 4, 5 languages, as many languages as you want, you will quickly realize that you will run into a scalability issue. The number of parameters and the computation requirements that you need will actually grow quadratically. So to understand this, you have to realize that when you build a code switch of ASR decoders that have the capability of switching from one language to another, essentially what you have to do is to take all the words in your graph, in your decoding graph of one language, and to connect it with all other words of the other language. You can do this efficiently in the FST framework with this notion of epsilon arcs, right? So you have a kind of bottleneck that will factorize everything very nicely. However, if you look at the classical pipeline, you would build an ASR decoder. So here I've taken an example with K2. The epsilon arcs are actually removed along the way and leading to basically an expanded graph. The reason we are removing this epsilon is for basically practical reason, for efficiency, because when you have this epsilon, the implementation of the decoder is more complex. And especially if you want to run on GPUs, the parallelization becomes more and more challenging. So my research question is very simple. If we want to build ASR decoders that scales linearly, so to speak, with the number of languages you want, can we actually bring the best of both worlds, having in one hand a factorized language model, and yet being able to parallelize it nicely on GPU? So the answer is yes, and I will basically present the theoretical result that allows to answer positively to this question. So all this work is grounded on the idea to represent a finite state automaton in slightly different way. So if you want to, so the classical framework is simply to put the labels on the arcs, and then you have your classical FSA, FST. So here we made a slight change, and we put the labels to the states, and the whole idea here is to decorrelate labels and weights. And then we have the adjacency matrix, but this matrix here can be an arbitrary semi-ring. So for instance, if you take this matrix to be in the log not the log semi-ring, sorry, the tropical semi-ring, then the decoder decoding, one step of the decoding is just one step. So one matrix vector operation will be one step of your decoder, and this is very nice because then it's very suitable for GPU. And on a small example, we're able to actually be 5 to 6 times faster than current implementation. But now remains 2 technical challenges to basically make this kind of scalable ASR, is how can we represent this notion of epsilon or backoff in terms of language model within this matrix FSA framework? And the second question is, okay, so now we have a matrix, but you know, LVCSR decoder is a very complex graph, which is basically composed of many elements. So how can we, within this framework, build the HLG graph? So, or rephrase it, how can we make this composition operation in terms of matrices? So the first theoretical result concerns the language model factorization. So here in this framework, what we found out is that the notion of epsilon can be considered as a factorization or low-rank factorization of the matrix. So here the T matrix, the matrix representation of your FSA, can be understood as decomposed in the following way. You will have S. S is a sparse matrix that accounts for all the n-grams you have seen in your training data. Then you have a low-rank matrix, U, that will connect all the emitting nodes to all the epsilon nodes. Then you have the complementary matrix, which is V, which is also low rank, and that will connect all the epsilon nodes to all the other emitting nodes. And finally, you have the E matrix that connect all the epsilon nodes together. So here we have basically managed things. So here things are compact, but there is something better, because now if you want to decode, remember what I said, decoding, one step of decoding is matrix vector multiplication. So when you want to decode, actually this low-rank factorization will make things faster, and you don't need to remove the epsilon. So the key thing, the key ingredient is just to choose carefully the order of operation. So very simple, you have to start from the right-hand side, and using the low-rank factorization, things will be actually accelerated. So here, multiplying the state vector with U will propagate the tokens to the epsilon states. Multiplying with E will continue this propagation to the epsilon state. Multiplying with V will actually broadcast to other emitting nodes. And the last step, adding S, multiplying S and V and adding all together, will make the final step of propagation, taking into account the n-grams. So here, the first theoretical result is very pleasing. We can actually have decoders that are factorized with the notion of backoff, help with the epsilon state, and we don't need to remove them at decoding time because this low-rank factorization can actually accelerate the decoding process. So the example I've shown you is actually only valid for bigram, and if you want to actually generalize for arbitrary n-gram, Andre here found a very nice formula so that you have here. All right, so second question was, how can we actually now build this? So far I just have the language model matrix. I now still need to compose it with a lexicon, with the HMM, so I need to find a way to compose things. So it took us actually quite a lot of time to figure out how it can be done, but we finally found the formula, and here it is. So it's maybe not very easy to appreciate it at first, but so anyway, I won't enter too much into details right now, but there are eventually important things that are to be considered here. First of all, your matrix will be huge. I'm talking about millions by millions matrix, so you want to have it sparse. And the good news, it's very sparse, but even though it's sparse, it's not very, very lightweight. So eventually, if you allocate this matrix, you build your whole HLG graph. What we found is that the resulting matrix was slightly a little bit bigger than the normal K2 matrix. And this is expected because we don't really have the determinization mechanism. But what is another important remark is there is a structure in the matrix and a redundancy. And this structure and redundancy can actually be used to make the decoding very efficient and very memory friendly, let's say. So the key idea is that your decoder matrix, after the composition of the HLG, basically you have a structure, but the vector, when you decode, remember matrix vector multiplication, the vector bears basically the token of your decoder. And this vector also has structure. And using the structure of both the matrix and the vector, we can actually calculate the result without ever evaluating the matrix. So this last equation is telling you something a little actually funny. It tells you that you can make one step in your decoder without ever evaluating your decoder. So in a sense, we have a lazy composition, dynamic decoder, and we have built it only using linear operation, matrix vector multiplication. So all here is actually super, super friendly if you want to scale up with a GP. All right, so I was hoping to show you some numerical result, but it turned out that implementing a full-fledged decoder in a workshop is a little bit challenging, given the time and the student asking questions. So, well, things are in progress, and hope we are actually trying to build now a 5-language decoder, and actually we hope the result to come soon. As a takeaways, I want to remind you that using the current tools, building a multilingual decoder is actually non-trivial. Here you have a lot of reports about having 2 languages, but code switching is rarely only 2, it's often 3. You have dialectal variation. It's actually a much more complex problem. Ahmed was mentioning that there is a soccer World Cup in Qatar coming soon, and there will be more than 2 languages to deal with. So that's just 2 languages is not enough. And to scale up with the tools we have is actually very difficult. So here I just wanted to point out that we have also alternative, we have also ways of representing the FST, which are a little bit unconventional using this matrix vision, and yet that can be very performant and make the whole process, the whole building of the decoder much more scalable. So thank you. I'm sorry, I thought I had a question. So thank you very much for your attention, and I leave the floor to Andre, who will talk about evaluation tools for code switching ASR.
So hello, my name is Andre, and I would like to present you a tool that we built to help us understand the output of our code switching models. So when we build ASR models, we typically look at word error rate, insertion error rate, substitution error rate, deletion error rate, and things like this. But when we are faced with new data set, new language, and we get word error rate of 50%, what does it mean? Is it good or is it bad? So we need to look at the output of the model. But this seems to be quite challenging when you are faced with multilingual data sets and code switching, because sometimes we don't read all scripts. So we need to build a tool that will help us understand the output. So let's consider this example from Telugu and English ASR model. If you just look at it quickly, you can't tell whether it's good or bad. If you add some color coding, you can see that the green parts are correct, red part is deletion, and the yellow one is substitution. You can also see the pronunciations of these words. And if you look at pronunciations of police and the corresponding Telugu word, you can see that the pronunciations are similar. So it's possible that these two words are transliterations. And in fact, police lu is one word that was split into two words following transcription guidelines. So these types of errors will inflate your word error rate quite a lot. So if you get 50% word error rate, it doesn't mean that your system is bad. But to find these errors quickly, we needed this tool. So as you would expect, you can get results like substitutions, insertions, deletions, or word error rate. You can also get the most common substitutions. So as you can see, police law is the most common substitution. We can then filter utterances with these examples. We can look at insertions and deletions. If you paid attention, you would notice that police is also very common deletion, but most common insertions and deletions are single letter words. So what does it mean? Let's look at some example. And here we can see example with YCP in English, in Latin alphabet, and YCP, a single word in Telugu script. So this is another source of potential inflation of the error rate. We can also look at transliterations. Here is example with highlight blue transliterations, but there are more transliterations saying Sonia Gandhi, and you can see it in Telugu, and always. So to be able to deal with these errors in the alignment procedure, we need to build alignment that is transliteration agnostic and word segmentation agnostic. So I will tell you how to do this in OpenFST framework. So this is our representation of YCP as 3 letters or YCP as 1 word. And within standard procedure, we would get 3 errors. Now let's introduce some FST operations, which will allow us later to do word splitting into letters. Then we can introduce substitutions and deletions. We can also introduce transliteration. So YCP in Telugu script can be transliterated as YCP in Latin letters. And then we can split these words into characters. And if we do this for reference and hypothesis, we get correct alignment telling us that YCP as 3 letters is the same as YCP as 1 word. And now I would like to invite Matthew to summarize our work in this package.
All right, so I want you guys to consider the landscape of bilingual speech. All right, in our presentations, we've addressed basically all of the different data scenarios and how you can cope with the lack thereof. So for instance, Dorsa described how we can make synthetic code-switched audio examples through the speech collage. Preeti and Ravi spoke about how you can use transliteration to generate synthetic text. Afterwards, Brian spoke about some code switching modeling decisions and how propagating the decision about language segmentation to the end can improve code switch ASR performance. Léa Marie then spoke about how using small amounts of data with self-supervised models is a good way to create code switch ASR systems. Luca described how we can scale up decoding to handle the whole spectrum of bilingual speech using a new framework for decoding. And finally, Andre showed you a nice tool that really made us aware of all the kinds of errors that we could see in ASR systems. And it really highlighted the importance of proper evaluation. And that's what the evaluation team is going to speak about next.
Hello, everyone. Okay, so in this part, we will focus on the question of robust and fair evaluation metrics for code switching. Here is our team who worked relentlessly for past few works on this problem. And during this whole project presentation, we have seen that the code switching ASR has the tendency to output cross-transcription, mistranscribed word, and among others, especially in the data set or language pairs where they use 2 different scripts. And this rendering challenge in the ASR hypothesis can affect the de facto ASR evaluation measures like word error rate. Next, please. However, if we remove this inconsistency and also compare with human acceptability judgment of the utterance, we can see a huge jump in performance. Next, please. So the main goal or the objective was to assess different metrics and find a fair way to evaluate code switching ASR, both in utterance and in the system level. So for this, we aim to benchmark all these matrices by correlating them with human judgment. But the challenge is, how do we quantify human judgment for utterance acceptability? And what metrics should we consider for the first tryout? Next, please. So from our, can you go back, Ahmed? I think we're missing, yeah. Anyway, in this work, we try to quantify the acceptability of the judgment in terms of minimal post-editing of the hypothesis. And for this, we designed a more fine-grained human annotation task. Next, please. So to create this corpus, we call human acceptability corpus for code switching. We sampled 2 hours of code switching speech, passed it through different ASR for getting the hypothesis. And then we took this hypothesis and gave it to 4 bilingual annotators so that they can do minimal correction to make the output acceptable. And all these ASR we used are pre-trained on monolingual data and that are different from each other by architecture or let's say decoding parameters. Next, please. So now we have a data, we have to select the metrics to test. We try to cover most of the common metrics that are used for ASR. However, with this, we also added 3 more approaches, like aiming to handle code switching challenges, like again, cross-transcription. The selected metrics that we choose cover different representations, such as orthography, phonology, and semantic space, along with different granularity, like a word, character, phoneme space. Next, please. So we have a guideline. We prepared that corpus for Arabic English pairs. Now, how can we ensure that whatever we prepared can be generalized across different language pairs? For this, we tried to adapt the guideline for Telugu and English pair, which is also an ongoing task of ours. Next, please. So the whole, just to summarize all our effort, we want to develop a corpus of human judgment quantified by minimal edits of different ASR output. We then benchmark the performance of the selected metrics for their capability to correctly evaluate code switching utterance and of course to evaluate the system. We try to ensure our work's generalization capability by adapting the annotation guideline to another language pair. With this, I will end the overview, and now I would like to hand over to Inji, followed by Omnia and Amer for more in-depth discussion of the metrics and the data preparation. Inji, to you.
Thank you, Shamor. So now we're going to go into details for the corpus creation. So we have 3 main rules for the annotation guidelines. The first rule, thank you, Amir. So the first rule, which is the rule of script segregation, this specifies restrictions on the script choice. It states that words shall either be written in Arabic or Roman script and not a mix of both. The only exception is the morphological code switching, where Arabic parts should be written in Arabic script and English words can be written in either Arabic or Roman script. Now, the second rule is that of acceptable readability, and it states that a transcript should be found acceptable as long as it's readable enough to allow someone to reproduce the original audio and intended meaning. This means that multiple answers are acceptable. And this is where the minimal edits rule comes to restrict that, stating that annotators can only do minimal edits on the character level. And this means that cross-transcription and spelling variations should be acceptable as long as they do not break the rule of acceptable readability. Now, we sampled 200 sentences to perform inter-annotator agreement, and we have some nice numbers that we would like to share with you. So first of all, the average CER between any annotator's minimal edits, like any pair of annotators' minimal edits, is 8.3% for CER. And while we might believe that this is a high disagreement rate, it only reflects the complexity of the task, where word acceptability differs from one person to the other due to unstandardized orthography. Now, the second figure is the average CER between the minimal edits and the hypotheses, and this reflects the amount of effort done by the annotators, and we find it to be consistent across annotators of around 15%. And the last figure is where we calculate the average CER between the minimal edits and the references. And we see that although both transcripts are correct transcripts of the same audio, we have an average CER of 20%, and we also have very high word error rate, And this again highlights that CER and word error rate are inadequate metrics in this scenario. So next we would like, Amir, can we go back once? Yes, thank you. So next we would like to define what the ground truth error really is. So for identifying a hypothesis ground truth error, we define this as the character error rate calculated between the minimal edit annotation and the hypothesis. And we choose character error rate as opposed to word error rate or any other metric because it provides high granularity reflecting the actual amounts of post-editing that occurred and is in line with our guidelines. So now we go over the evaluation metrics. So first of all, for the orthographic metric, we covered the character error rate, word error rate. We also cover match error rate, which computes the probability of a match between the reference and the hypothesis as being incorrect. We also cover word information lost, which is an approximate measure reflecting the proportion of words that are lost between the reference and the hypothesis. And we investigate the use of transliteration. And on top of all of these metrics, we apply Arabic alif ya normalization as a variant on top of all of them. And now I give the talk to Umnia, who will tell you more about her work on transliteration.
Hi, everyone. My name is Umnia, and I worked with the evaluation team on using transliteration as another evaluation method for ASR. And so transliteration is the method of transcribing a word or a sentence from one writing system to another writing system. So either go from the Arabic writing system to English or vice versa. And the reason we do this is because, as you can see in our reference and hypothesis on the first row, we had a lot of cross-transcription, meaning that we would have, say, the words 1, 2, 3 written in an English script in the reference, and then the exact same words written in an Arabic script in the hypothesis. And so what this would do is yield a higher word error and character error rate, even though these words are the same. And so, as you can see in the second row, we would map everything to the same script to give us a better idea of what the ASR is doing. The model that we used to do this was the QCRI transliteration model, which is a phrase-based system trained using Arabic-English character pairs. And these pairs are extracted using a transliteration mining model. And it has a lot of features, including a phrase translation feature, a language model feature, as well as word and phrase penalties. Another transliteration model that we used was a FST-based transliteration model. And so what this would do is we would have a finite state transducer that takes in an input tape with symbols in one language, say Arabic, and then we would transliterate to the output tape, which would be their equivalent, their phonetic equivalent in English. And so in order to do this, we trained our FST on 12,877 transliteration pairs. And so this makes this method a bit more advantageous because we trained it on a relatively low amount of data. And this could work for low resource languages that don't already have existing transliteration models. And this is if you look at this example, we have on the first row, we have cross-transcription between the reference and the hypothesis. And then when we transliterated everything to Arabic using the QCRI transliteration model, we noticed that the word error rate dropped because word 3, say, maps to the exact same word. And then we noticed also a drop in character error rate. And overall, you can see that using either the QCRI transliteration system or the FST-based transliteration system, helps us see that the words actually have a lot more in common than we previously thought. And so I'm going to pass it on to Amir.
So the next we are looking on phonetic. So why it's important to consider phonetics. Main motivation is transliteration. Do not consider the pronunciation similarity. Why pronunciation similarity is important? In many cases, when we have accented English, we have a lot of cross-transcription. So the model switches completely to another language. And here you can see why the reference is in English. The model completely switches to Arabic, but in phonetics, they look very similar. We also have a lot of cases when you have out of vocabulary words, and the model just predicts the most likely BPE units, the subwords, And we end up with these funny examples where the model actually glues the mixed BPE units from the two languages. Again, looking at the phonetics, they look very good. So with phonetic similarity, we want to measure how good the model in pronunciation while giving only partial penalty for just using the wrong script. So we first map everything into the shared phone space. We use IPA, International Phonetic Alphabet, since it supports a lot of languages. We measured the similarity using the Hamming distance, which basically counts the positions at which the two phonetics features are different based on the articulation features. And on the side, you can see the sample of some articulation features that we are considering. And then we penalize the substitution. Instead of just having an integer number, we penalize it partially by this dissimilarity between the phones. So here's just an example of how phonetics handle the cross-transcription. It has also some effects of orthographic standardization. So people who write Arabic in different ways, they still try to be faithful to the phonetics. And also we can handle the mixed BPE from the two languages. This is just an example of the matrix edit distance. And you can see that for the two sounds, the A and they have the penalty of the substitution of the partial cost, because in the phonetic space, they are very similar. Next, I will handle this to Inji to talk about the semantics.
Thank you, Amir. So for the semantic similarity, our first idea is to calculate the cosine similarity between the reference and the hypothesis. And then as a second step to that, we also investigated translating the reference and hypothesis first into Arabic or English, and then calculating the cosine similarity. And the motivation here is that we found that words that have cross-transcription issues, such as national schools in this example, some of them got correctly translated into English through Google Translate API. And the second motivation for using cosine similarity is that words with different scripts or with different spelling variations should still be closely represented in the embedding space. And so into more details, we translate the references and the hypotheses into monolingual Arabic, English, and even Japanese as a very independent language. And we keep the original sentences as well. And for the 4 language setups, we calculate the following metrics: BLEU, CHRF, BERT score, and cosine similarity. And for cosine similarity, we investigate the use of CLS token and mean pooling over tokens embeddings, where mean pooling outperformed a CLS token. And we also found that we get actually higher correlations when we aggregate the scores of the different metrics across. No, Amir, can we? No, not thank you, Amir. When we aggregate the scores of those metrics across the different language setups instead of relying on only one. And now we go into the results section. So the first evaluation we performed is a sentence level correlation evaluation. And for that, we present the correlation scores between the ground truth error, which is the gold CER calculated between the minimal edits and the hypotheses, and the scores provided by the different metrics that are calculated between the hypotheses and the references. And here we only report the most significant results, and we report that in descending order of correlation. So next, please, Amir. For the transliteration, we find that transliterating into Arabic script followed by normalization gave us higher correlation than transliterating into English. For the phonological similarity, we find that PSD outperforms the conventional PER metric. For the similarity metric, we find that cosine similarity gives higher correlation as opposed to the other metrics. And the nice thing is that the three approaches that were investigated actually give higher correlation than the conventional CER and word error rate metrics. Now, for the second evaluation, we performed a system-level evaluation. And in this evaluation, we want to assess the ability of the metrics to provide correct ranking across different systems. And this is very important because this is what researchers are going to rely on to make system-level decisions. And so for the 3 systems the 3 ASR systems that we had in our experiments, first of all, we calculate the overall gold CER across all hypotheses for each system, and we use that to get the ground truth ranking across the three systems. Afterwards, we calculate the overall scores provided by each metric for each system, and we compare the rankings. And we find that all the metrics were able to provide us with the correct ranking as the ground truth one, except for CER when applied on the original sentences. So now, in order to conclude, our contributions are as follows. We design annotation guidelines, we develop and release or will release our corpus, which is the Human Acceptability Corpus for code switching. We evaluate a large number of metrics covering orthographic, phonological, and semantic similarities. And next, please, Amir. And the takeaway points are, we find that word error rate and character error rate are not adequate for evaluating cross-transcription scenarios. And therefore, we look into transliteration approach, and we find that it does not consider pronunciation similarity. And then when looking into the phonetic metrics, we find that they fall short against capturing the meaning and semantics. However, when going into the semantic metrics, we find that they're currently limited by the current performance of code-switched machine translation systems. And therefore, we believe that a good way to go from here is to actually exploit the complementarity of metrics to reach a more robust and fair metric. However, it is to be noted that in the case of low resource language pairs, a challenge here would be to find the available, to find available the resources needed in the investigated metrics. And finally, for future work, we're currently working on replicating the experiments on Telugu English. We're also working on extending the human judgment annotations by adding a second step focusing on acceptable writing styles. So instead of the annotators accepting transcripts that are only reproducible and understandable, they should also be acceptable in terms of the choice of script and the choice of spelling. And finally, we look forward to continue working on improving evaluation metrics, where we would like to either investigate aggregating existing metrics to exploit complementarities or introduce and analyze a new metric. So thank you very much for listening from the whole team. And I give the talk back to Ahmed.
So it's 12:05 now. I guess we can take a few minutes for question answering for the ASR modeling and evaluation. And before we go into the wrap up,
We have also a question from Samuel.
Can you say it?
Samuel. I don't see it. Yeah, like maybe so.
All right. Okay. Do you have a question from the audience? Go ahead.
In the speaker about the code switch synthetic audio, I was surprised. I think I read it right. There was a big gap between the synthetic data and real data. Is there some speculation of why? The examples didn't seem that weird. Of course, I don't really know, but it just seemed like a really big gap. What's going on?
You mean the audio was not natural?
No, it's when you used to train with it, it didn't work. It didn't work. I mean, it gave it help, but it didn't help nearly as much as the real data, is what I recall.
So what is for the hybrid or for the end-to-end? The end-to-end.
I think it's not a matrix. Like the top line numbers are like 18-20%.
Yeah. Okay, I'm just. I need just to. It's okay. I mean, don't worry. Yeah, that will be the hard part. So, okay.
I'm just trying to ask you in the talk.
Almost there. Just give us 1 second.
You got it.
Sorry, we have a lot of slides. Almost here. Yeah, that's on. Excellent.
Yeah, exactly.
How is the actual video? Huh?
It's 50 hours of monolingual and 60 hours of
For the actual one? One thing that I guess I had a thought about is that the fake audio switches every speaker, and that's I guess that's a lot of artifacts added to the data. Also, it wasn't that much. It was only 50 hours. Maybe that's why.
How much was the real?
Oh, 60 hours.
So that's not that different.
Yeah, I guess not that different.
The difference is that the fake code switch audio is recycled from the monolingual data. So the acoustic diversity is not increased. Whereas if we use the real code switch audio, we have 60 hours of extra code diversity.
Oh yeah, that too.
There are also some artifacts. It's unclear whether they help or hurt. You think that should help, right? It would be like a cube. But it's not present in the test. You never know. Sometimes it's not present in the test, though, right? So that it would.
And also, these models might do an on-speaker continuity, for instance, to help things.
I think it's also related to the way they synthesize the audio. I remember that you have one slide playing the big audio here. So the quality of this exactly is very low. I think there's a lot of the artifact from TTS as well.
Do you want to play it?
We did. It sounds like
on demand.
And it's also the inconsistent between speaker switching. So they can use speaker information to predict the code switching as well. But in the real case test, there's never have this clue. I guess those mismatch also cause the gap as well.
There could also be a small issue. The alignment is not necessarily perfect. So there can also be some small alignment.
Yeah, I also remember the last when you played, there's a cutoff in the last words.
Yeah, it didn't say shall.
你的 broadband
And the last words cut off.
I think that's the alignment.
Right. So these are all multiple things that we have to make our assumption to get something off the ground. I mean, ultimately, we should mind the gender, the speaker factorization into this, because not every language diarization has a speaker diarization. So all these things should be considered as part of when we generate audio at the end. So maybe we should mind the gender, ultimately should have L1 and L2 from the same speaker. So all these kinds of things would have been the ideal scenario and the audio augmentation that we ultimately would like to do for the experiment of benefiting from audio generation.
I guess it's a chicken or egg, but you could train a multilingual code switching TTS system too, right? Principle with your data.
So we considered using TTS or using voice conversion, but a lot of things could have been done in these 6 weeks. We thought of the simplest way of gluing, because ultimately we would expect this to be part of the data pre-processing or feature extraction. If you are building a vanilla ASR, you can say you can have an option. Oh, I want to have a TTS, and the data generation will try to augment some TTS.
One thing that I wanted to add, this second paper actually built a code switch TTS system. That gain was very close, like maybe very comparable to like the splicing method, and that's easier to do. Takes less computation and data, so that's why we kind of went with that also.
And just a comment about that. Actually, the TTS data augmentation, code switching, or whatever, I also observed something similar, especially for the end-to-end system. My guess is that the end-to-end system is, with this kind of data, anyway, somehow ignore the encoder part, but the alignment part or the decoder part is well corrected due to this kind of data. For example, TTS data augmentation, people imagine that one speaker can actually improve performance, but it's actually single speaker TTS data augmentation is good enough. We may have some small improvement by using a multi-speaker. So again, this is usually my kind of guess is that the alignment part, attention part, the decoder part is well correct based on this data augmentation techniques. And I feel like partly this result is also showing that quite well.
All right. Sounds good.
Also on this slide, I wondered about non-concatenative synthesis.
Sorry, can you say that again?
The non.
Yeah, so you asked her about whether you could do better concatenative synthesis like festival.
Yeah.
There's a lot of neural synthesis now as well.
Yeah. That would be like, I guess, a future direction to try. We haven't tried it yet.
The reason we mention concatenative synthesis is this is the old way of doing TTS. You glue things next to each other, and then it's supposed to a ready-made post-processing that we don't have to reinvent it. Somebody have figured it out in the concatenative TTS, which is the neural TTS is slightly different. That was the reason to consider the physical TTS in this.
I guess the problem is neural TTS might not work well multilingually because it wasn't written.
You might not have the data. And also that first paper that Dorsa mentioned, that they actually found that doing this concatenated approach through TTS, there's a lot more speaker variability and acoustic variability that you get. And it showed that actually does help.
And also,
so I know Shidri is saying that only the decoder and attention are trained, but we also had the CPC model, which is only implicitly doing these things. And there was also a lot of improvement there. So I think a little more is going on. And using TPS, you'll have very low speaker variability. Sorry.
One thing I was going
people can hear you. Yes.
Yeah, one thing I was going to say is there's another paper that I didn't include here where they used like an existing TTS system. I think it was Baidu or something to generate code switch audio for like the training, and that one had less efficacy. I'm pretty sure it wasn't as helpful using it. Yeah.
So I was thinking that for your method, I saw that there was like a mixture of male, female, because you were just focusing on the words, let's say. So would it be better to have, let's say, it's female, all female, or and also trying to do like some post-processing because in the edges you will have this artifact effect of just like gluing two parts of audio together.
I mean, yeah, the six weeks, I guess, of the workshop is not enough time to do all of these things, but we did consider like we tried the energy. I guess this was like one of the first things to do, but I mean, yeah, we were thinking about normalizing over like gender and some post-processing to make it smoother, but we like haven't had enough time to explore that direction.
So in the part you're talking about using joint monolingual models to predict like the token-based level for the ASR and then pushing the disambiguation of the language downstream. In situations where you didn't have like where each language's like posterior probability was the interval or the difference in those was not very great. It was hard to disambiguate. What strategies did you look at for trying to choose in ambiguous cases? And also, I don't know if you going on the earlier question about like there's different levels of code switching engaged in by different levels of multilingualism. So like a balanced bilingual might have full command of the phonetic library of each language and would say something with a native speaker accent, whereas a more imbalanced bilingual might use the phonetic, the phones of their native language to produce a word in another language, which would maybe be, I would imagine, harder to disambiguate because you get a higher probability in the other language. What approach do you think makes sense to try and disambiguate those?
Okay. Thanks for the great questions. There are two questions. So
yeah, sorry, this is a lot.
thank you. The first question is, in the case where we're attempting to jointly model monolingual and code switch speech, and you have a case where you can't actually produce the language segmentation reliably, what happens in this case? In this case, actually, you can see that it worked. I think the reason that this worked is because it was able to see that the Mandarin side was slightly less confident than the English side. But is that reliable? I don't think it is. So when we're training these joint models, key point is that we're just doing a very simple additional fusion here. And so actually, the bilingual decision is just going to look at both sides and make a very simple choice. I think you can consider more sophisticated fusions there and introduce more parameters to learn something. I could see that the performance might be better, but at the very least, I think there's also a risk to doing so. So we've tried this on a different data set, which was very imbalanced. 80-20 Mandarin to English. And what happened there is if you learn that it's 80-20 very strongly, you can do well on the 80-20 speech, but on the English side, you end up suffering a lot. So yeah, the decision of choosing which side is being spoken sort of depends on the bilingual module being able to look at both and decipher for each frame which language it thinks is being said. I hope that sort of answered your question. I think the second question was more about the phonological differences when you're having code switch speech. You're probably not dealing with L1 English and L1 Mandarin. I think in this data set specifically, you have English being spoken by L1 Mandarin speakers, and there's some accent. Yeah, and I think it's a great question because it changes the picture about data a lot. So is the right English data to use just libre speech, or should it be like accented English data? And yeah, I think it's very important to consider the accent differences. It changes a lot how well you're able to differentiate between the two languages. Yeah, so that's my answer. Yes.
I think also Brian's method where he purposefully trained the monolingual models to produce.
You also have an online audience.
Yeah, sorry. But Brian's method where he was purposely training the monolingual models to produce these transliterations, i.e. what the Mandarin model thought English sounds like and vice versa. There is some notion of the accent or modifying the units to be suited for the particular test set that you're working with. So in some sense, I think this training scheme, it is adapting whatever you thought the monolingual pronunciations were to now the code switch scenario. So you know, you might have the word how you, and you think that corresponds to some canonical English pronunciation, but now we also see that it corresponds to some sort of Mandarin acoustics. So now there are Mandarin acoustics that affect the model for how in English and you in English. So if someone is now switching seamlessly between languages without changing their pronunciation, it could be captured here. And if they're not, well, then there's no problem that this in the first place. Like the model would be very good at distinguishing languages.
Online question.
Yeah, I have one question to Brian.
I think you're breaking up, Jinyu. Would you like to say it again, maybe?
Okay. Maybe my internet is not good. I mean, with the later decision, it's easy for you to integrate external language model, and definitely you'll get a very good accuracy. But I'm wondering why, without language model integration, you'll also get a better accuracy than the early decision.
Yeah, great question. So when we're pushing the language segmentation later, one aspect is that we said that we can use the external language model to help us decipher. But in this picture, there's another bilingual module, which is the CTC module itself. And that CTC module is trying to decipher Z given ZM and ZE. So when we train the model with a later decision versus the earlier decision, you can see that in the earlier decision setup, the P of Z given ZM and ZE is very easy during training. It just needs to see that it's a null token on one side, and then it must be the other side. But when we gave it the later decision setup, then this bilingual CTC module itself becomes more sophisticated. It has to consider the cross-lingual confusions.
Okay, thank you.
There are some objections to my answer.
Since you're on this slide, let's ask a question about your factor graphical model and the equation over there.
Yeah.
Is it to mismatch between them?
Yeah.
So, So on the left, on the graphical model, so the y depends on the z and z, right? But on the right side, I'm pretty sure that doesn't show that.
Yeah. Okay. So the question is how to get from the left side to the right side with the factorization. So thank you for the great question. So we make two key independence assumptions to achieve the factorized form. The first is that these two terms representing the monolingual decisions, we say that they can be made independently of each other. And the second is that we say that given ZM and ZE, we can perfectly determine Z without any additional information from X. So with those two, we're approximating the left side in the factorized form. I think the first assumption that we can make these two independent of each other, you could say we should soften it. And I think there are ways which I'm interested in sharing the information between these intermediately to soften this independence assumption. And the second independence assumption is that given Z, M, and ZE, we don't need any information from X. We tried to validate this experimentally by including additional information from X directly to the bilingual module. And we observed that actually nothing is, no additional useful information is captured by doing so. So it's just one experimental view of it, but we think that those assumptions may be reasonable to achieve this form.
Got it, thanks. There's other slides. I was also confused with the location. We can go 270 something. Oh yeah, maybe this slide.
Okay.
So your y hat here, y hat m, and the ym is the notation in the graph is zm, ze.
Yes, hi. Thank you very much. He's great.
Oh, okay. So the question is, what's the relationship between the ZM and ZE shown in the graph on the left, the figure on the left, versus the training targets YM and YE on the right? So I should have explained that these Z's are the alignment, input to output alignments produced by CTC. But to train CTC towards producing these alignments, we train them to maximize the marginalization over all the possible input to output alignments, where the output is represented by Y, this label sequence, instead of an alignment sequence.
Right, I see. So the YM is also depends on the ZM, I guess.
Correct. Yeah.
Because you're only trying to another question. So one of your slides also show, I guess you show for the length segmentation term, you say you remove I think the YX term, yes.
Yeah.
So you remove that term, it's due to 2% reduction of smoothing. So that term depends on the whole sequence. So the X here is the whole sequence of X.
It's the whole sequence.
Right, so,
well, no, it's the whole sequence, but then it's making a frame level decision.
I understand.
Yeah.
So in theory, so the left segmentation should help for the ASR. The reason it does not help is you look too long to make decision based on the majority of the token you're fitting characters instead of local. So instead of removing this term, why not modify it? So look at some local segment.
And that's a cool idea. Yeah. We removed it because it was an easy thing to do. It was more to analyze like what's happening implicitly when you don't factor these out. Why are things breaking? And it's because implicitly the model is making a decision about which language should be present the whole way through. And I think we just showed very explicitly that if the model's making errors, it's not necessarily making phonetic errors. In fact, if you only look at the phoneme term, you do better. The reason it's making errors is because there's some bias towards language, which if you didn't have this factored approach would show up directly in the phoneme predictions themselves. Again, like it's a technique. It's interesting that it helped, but I kind of view it more as a tool for analyzing sort of why delaying the late decision and using the language model information at the end helps. But I think that's a very interesting idea. And if we just limit it to local decisions, I think in the future work we said we should do something with this LVX factor here to adapt to new domains accents. So that's a good thing to try. Thanks.
Sorry, last question. So on another slide, you show the factorized language model.
Factorized language model. Is that Luca? The decoder?
Yeah, that's a factorized language model. So I think that's an interesting way to formalize this code switching problem. Can you show me the slides that you factorize that?
Just stop me when it's the right one.
So let me get this one. Yeah. So I was wondering the physical meaning of the epsilon here. The reason why I asked this question is to remind me. So the industry, there's a problem. So when you do the speech recognition on the phone, so when you say you open, so play A music, play B music, or call person one, call person two. The way the industry people does is, so they also have a similar issue like code switching, because all the your contact list on your phone is from different languages, and all the music you play on your local device is from different languages. So they have similar issues. Very similar to code switching, but it's similar. The way industry people does is they put a tag for those music or context lists. So instead of recognizing play A music, play B music, they put a tag. And so whenever they recognize this is a music tag, so they put out, instead of building background for play A music, play B music, they put out all the unit graph from your local device and jump into that, and it only depends on your acoustic feature to recognize those those music or your phone contact list. So that type they use, they call it I think it's called it classical class language model, which was invented by Peter Brown decades ago. And that tag is very, I think it's related to the epsilon you described here. I was wondering, what is your explanation of why you think this factorize this hidden space epsilon? What does it mean? What's your understanding of that?
I'm not sure I understood the question, actually. If you should just make it like
so how do you generate the epsilon when you build in the graph? So you have so when you generate this graph using FST, you have the H, you have the L, you have the G.
Yes.
So the H, when you play this code switching, your H is come from different language alongside, right?
Yes.
Your H is definitely going to be proportionally large when you try to do the code switching, generate multiple languages. But the issue is the G here, right? The G is become exponentially large when you allowing the switching between one language to another languages. And the way you do that, you try to do is factorize those big matrix transformation
yes.
to low rank, right? And this low rank, I think this has a physical meaning. If you have introduced a physical meaning of those low rank, and you can feel that this linguistic or other behavior constraint to it, maybe even more efficient than just data-driven to factorize the matrix because it's too sparse. I'm wondering you never have enough data to train this low-rank matrix approximation.
It's actually more like a general thinking, so I don't know if I can summarize it as a question, but eventually I will comment on it. So I think you have several ideas and you're pointing at the right direction. I just move one slide further to the next slide when I do actually the composition. And actually, it's not a composition, it's a replacement. So actually, your idea of having a tag, of music, like you need to know that now you're looking for a music entity, and then at the last minute, you will actually put your model there. This is actually exactly what is happening. It's not a classical composition. Classical composition exists within the matrix. We have also the algorithm, but it's in this case we are not building HLD by composition, but by replacement. So that's actually fits very well your idea. Regarding the factorization of the matrix, how it happens when we do this kind of replacement, if you look at, so there are a big sum here, the big term, which is not so important here, but you see the TG matrix. The TG here is exactly the factorized matrix I was showing earlier here. So in a sense, you see you have a big matrix, a TG, the factorized language model, and some other matrices. So in a sense, the epsilon of the TG matrix are somewhat protected or like encapsulated within the factorization. So they won't actually play or change anyway the composition. You have a factorization of the matrix, and you can basically, here TG, I can use the expanded matrix or the factorized matrix. It doesn't change anything. So the epsilon here is more a convenient way to represent this factorization, but it truly doesn't exist. My matrix has no state epsilon here. My matrix is a number of emitting states. So if I move back to the to this example, so my matrix on this example has 6 states, like 3 English words and 3 Mandarin words, and the epsilon are just to illustrate this. Too late. So I just finished in the word. So it's just about to represent the factorization, but not corresponding to any physical things. So I think it's over now.
Okay, I'm going to ask what I already put in the question and answer, so it's not any different. When you were talking about I don't know, about a half an hour ago, one of the speakers talked about some ways to smooth the input, the training data, and what occurred to me is that perceptually, one way to do that is to add a little bit of noise. So I've just sent about 5 or 4 articles to the group in general that shows that human perception improves actually when you add noise. That sounds counterintuitive, but it does happen. And it happens in a variety of cases. And some of the cases are where, first of all, because speakers change their behavior when they're in noise. They speak louder, more clearly, their spectrum brightens and more energy towards the high frequency. And all of those things actually enhance intelligibility. So there's a speaker effect, but there's also a listener effect in that when speech is interrupted by either code switching or by literal interruptions, if you add a little bit of noise, everything sounds smoother and everything sounds more natural. If you have very slow speech like this, which is incredibly annoying, if you add a little bit of noise to that, it sounds more natural. And so I was just wondering if anybody tried that with the data sets. And one question that came back was that we don't think a machine learning algorithm would care about that, and that any additive noise would be a detriment to the data set. However, my thought there is that these models should be prefaced by some biologically inspired model of the cochlea. If you had that, then adding noise would show its effect as a good thing sometimes in certain conditions. That was my question. So the real question after all that was, let me see if I can go back to the original question. It was very simple. It was, has anybody tried this in terms of adding a little bit of noise to the data set, which might smooth out any of the discontinuities caused by code switching or any other environmental noise?
So thanks for the tip. The answer is short. We have not looked at it, but I think it's very interesting to look at it in the future work. I think it's very interesting. And thanks for sharing the papers. I will definitely consider them.
My pleasure.
The work that Dorsa is doing is actually could potentially lead to a paper. So apology for running way over time. I would like to summarize in the next couple of slides. Now you have seen what we have looked at. We tried to make the problem more practical from the point of view on having a problem that we code switching that we don't understand to generate text that we cannot evaluate. And the way we looked at it is what can we understand in motivating code switching. We looked at different things, but one of them where you have gone relatively vertical is the formality. We've seen the work from Devashmita into this. We tried to look in the multilingual code switching into the practical cases. We have looked at plenty of languages, South African languages, Bengali, Mandarin, Hindi, dialectal Arabic, and Gaelic. We looked at multiple domains. We looked at the same language in more than one domain. For the textual audio augmentation, we look at generating using lexical linguistic rules, pre-trained, and also training network using a small amount of data. For acoustics, you have seen the work from Dorsa in the speech collage, in the ASR. We just had a long discussion about how we looked at the decoder, about the modeling for the efficient search space, and the data pre-processing. Toward the optimal robustness, you have seen the challenge with the output. This is the first time to look at human acceptability of a code switching multilingual ASR. We are moving toward human readability. As you have seen, there are a lot of things we have looked at, but we have not solved many of them. So, we're not naive that we are not expecting really to solve this in 6 weeks. So moving forward, we have thought on having momentum on this work and push this to the next stage.
So at the moment, we have the multi-genre code switching benchmark challenge. This is to be announced in SLT, happening in January next year. So bear with us, and we expect to have a place. Again, the motivation here is to ask the right questions and to go for multiple languages. We have a great effort happening in the Indica challenge. There's a great effort happening in Mandarin, but again, we are trying to look for problems where we address things like what Ken has mentioned, just adding a noise to the code switching, because the nature of the speech is very challenging, could help. This will happen in SLT. This is thanks to the great team that we have been working with us over the last 6 weeks. We had a lot of work and also a lot of fun. We had many visits. Just I want to highlight on the third picture on the top, this is us yesterday bowing to Dabashmita, because Dabashmita is our colleague in Hong Kong. Always we have to connect with her at an inconvenient time. But yesterday was the time where we are all sitting here late, and it was a convenient time for her. So finally, she managed to get her revenge. I'd like to thank everybody for the great workshop. One final announcement, that we have a SLT happening in Doha January next year. And one of the interesting activities is we'll have the code hackathon. This is quite new. There an attempt for doing this before. This time we'd like to do it with focusing on languages of the world, which align with what we are doing. Please consider participation and join us into this. If I can take 1 second by asking colleagues who are remote to show their video, then we can thank them. Thanks to NG, Preeti, Ravi, Sunaina, Davashmita. Right, which one? And stretch it. All right, just I would like to thank our colleagues who have been working in very inconvenient time and managed to join all the meetings. And I'd like to end here.
Right, you don't get to go yet, because I have a few things to tell you before I dismiss you from here. So let's stop this guy. And let me quickly get back to something else that I want to share with you. Okay, well, we'll just do it this way. So you've all heard a lot of interesting presentations all through yesterday and today. In fact, this is more or less what you went through. More than 9 hours of technical presentations by more than 60 people working over 8 weeks, and actually even more if you go back and look at all the preparations that went in. So this was tremendous, and I'm very happy about it. What I want, Phil, first of all, let's give all these guys a big hand. As I've said many times when I make these presentations, this thing, everybody thinks of it as the summer workshop, but it's not just a summer. There's a whole lot of bunch that happens, all the way from, I think it'll start next week and go on till the next summer this time. So all these things happen mainly because a lot of people help us in the background. So the first set of people that I want to thank are Ruth, Lauren, and Dan. So Ruth, as you all know, is our senior administrative coordinator. She pretty much runs the whole workshop. Lauren helps her. Lauren's the new Ruth. And Dan is our sysadmin, and they're helped by these two student workers, Michelle and Callista. Now, I have to say something in particular about Ruth. Ruth actually retired this year from Johns Hopkins. And she's back in a part-time capacity because I said, hey, I can't do this workshop without you. And she'll continue to help us a little bit. But in some sense, next year we'll be in Le Mans. So this is, in a real way, Ruth's last work. She retired only recently, so all through the preparatory work, she was helping us. So this was sort of her last workshop as a full-time person. So I want to particularly thank Ruth for all the work she's done over the many, many years to make these workshops run well. Thank you, Ruth. The second part, which is also equally important, is that other than the people who make it happen, there are organizations that make it possible. And as I mentioned to you in the opening presentations, we had leftover funds from 2020 because 2020 went virtual on us unexpectedly. So we used money from Amazon, Google, and Microsoft. And this year we had the European Commission's Esperanto grant supporting one of the teams. So those are for sponsors. So let's thank our sponsors. And running something like this, you need a lot of inspiration. You need people to sort of make you believe that this is a good thing. And so whenever I think about, now this is a little bit more personal, I think about people whose spirit is watching over us. So the workshop is named after Fred Jelinek. You all probably have heard about him often enough. We lost 2 other colleagues in the last 2 years, in the last time since we had the workshop. So Jack Godfrey passed away in 2020, and he has been a big influence on Hopkins and on CLSP and on me. So thank you, Jack, and thanks for watching over us. And also very recently, 3 days ago, another giant in our field, Sadaoki Furui, passed away. So maybe I'll just take 10 seconds to remember them, and you can remember them with me. Thanks. All right, moving on. We're off to the races. 2023 will start again, as I said, very next week. And the JSALT workshop is going to go to Le Mans. So hopefully some of you will come there again, and others who are listening online will say, hey, France, that sounds like a better idea than Baltimore. I personally think they're both good, but you're welcome to propose something in September or October, come to our planning meeting in November, then put together a team in December, January, and we can start working towards 2023. So that's pretty much what's in the distant future. In the near future, there's a farewell dinner. So we start at 5:30. We'll be in Gilman Hall. This is a 1920s building, so more than 100 years old. Of course, that looks like an old black and white photographs. The building is actually much more modern, like I promised. So this is the atrium in which we'll have dinner. And in case you can't put this modern picture together with the old one, this is what it looks like when you look at the tower from inside. So see you all at 5:30. Thank you.